Look up at the night sky, at those pinpricks of distant light, and for a moment, let yourself truly envision it. Picture a fleet of vessels so extraordinary they seem ripped from the pages of science fiction, sailing on beams of light, powered by miniature stars, or harvesting fuel from the emptiness between worlds. This is not just a fantasy, it is a future that was meticulously designed, calculated, and dreamed into existence by the most brilliant minds of their time. Yet, these breathtaking concepts now reside in a quiet universe of filing cabinets and forgotten digital archives, their potential forever untested. It is a startling but true fact of our journey to the stars that for every single spacecraft that actually makes it to the launch pad, dozens of these revolutionary, mind-bending designs are abandoned. They are the ghost fleet of human ambition, the blueprints of a tomorrow that never arrived. Today, we are opening that archive. This video is a journey into the captivating and often poignant world of 25 mind-bending spacecraft concepts that were shelved too soon. We will explore the incredible stories behind these lost marvels of engineering, from colossal interstellar arcs designed to carry entire generations to visionary engines that promised to harness the power of antimatter. Each one represents a fork in the road of our cosmic destiny, a path not taken. We will uncover not just how these machines were supposed to work, but why they never left the drawing board. What does it say about us, about our ambition and our limitations, that we conceived of these wonders only to let them fade away? What incredible futures, what new chapters in the human story did we lose when these projects were cancelled? These are not just questions of engineering, but of imagination itself. This exploration is more than a list. It is a testament to the boundless power of human ingenuity and a sobering lesson in the harsh, practical realities of progress. It is a story of what might have been, a chronicle of the greatest near misses and might have beens in the entire history of space exploration. From the depths of the Cold War to the dawn of the private space age, these concepts pushed the very boundaries of physics and challenged our understanding of what is possible. They are monuments to our eternal desire to reach beyond our grasp, so prepare to be astonished, to be inspired, and perhaps even to be a little frustrated as we begin our countdown to discovery. The journey starts right now as we prepare to unveil the very first of these incredible shelved marvels. Picture a vessel that completely redefines our concept of a rocket. Instead of a controlled chemical burn, its engine is a relentless series of atomic fireballs, each one a miniature sun detonated mere moments behind the craft. This was not science fiction. This was the serious, calculated proposal known as Project Orion. Emerging from the fertile and fevered minds of the Cold War era, this concept was arguably the most audacious and powerful spacecraft ever designed on paper. Its goal was staggering in its scale, to carry not just a small crew capsule, but an entire city-sized habitat on voyages across the solar system, with Saturn and its moons as a primary destination. Conceived by brilliant physicists like Freeman Dyson, Orion was a brute force solution to the limitations of chemical rocketry, a direct attempt to harness the raw, untamed fury of nuclear fission for the purpose of exploration. The engineering behind it was as ingenious as it was terrifying. At the rear of the massive spacecraft was a colossal, armored pusher plate, perhaps hundreds of meters across, connected to the main crew compartment by a sophisticated system of giant shock absorbers. The propulsion method involved ejecting specially designed nuclear bombs out the back, one after another, at a rate of several per second. these devices would detonate a short distance away, and the resulting plasma fireball would slam into the pusher plate. The shock absorbers would smooth out these violent, rhythmic impulses into a continuous, powerful acceleration. It was a form of travel one engineer described as riding a car with someone constantly setting off dynamite in the trunk. This pulse propulsion system promised something no conventional rocket could: incredible speeds. Theoretical calculations suggested an Orion Starship could eventually reach up to 10% of the speed of light, making a journey to a nearby star like Proxima Centauri a multi-generational endeavor, but a feasible one within the known laws of physics. For a brief, shining moment, it seemed like this incredible machine might actually get built. Teams worked on detailed designs, from smaller interplanetary versions to the grand interstellar arcs. They tested the pusher plate concept with conventional explosives on scaled-down models, which proved the fundamental physics could work. The promise was a solar system opened up to humanity, with missions to the outer planets taking mere months instead of years. Yet, the very power source that made Orion so potent also led to its downfall. In 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Test Ban Treaty, which explicitly prohibited nuclear explosions in the atmosphere, underwater, and in outer space. This single political act effectively pulled the plug on Orion's development. Beyond the treaty, a growing global consciousness about the dangers of radioactive fallout and the sheer ethical weight of launching thousands of nuclear warheads into space created an insurmountable political and environmental barrier. The project was quietly shelved, a colossal dream grounded by earthly realities before a full-scale prototype could ever leave the drawing board. The legacy of Orion, however, endures as a powerful reminder of a path not taken, a testament to an era when humanity dared to dream on a nuclear scale. While the Orion concept was about raw power, the next great shelved dream took a more refined scientific approach. It asked a profound question: if we can't send people to the stars yet, could we at least send our eyes and ears? The answer was Project Daedalus, a stunningly detailed blueprint for humanity's first dedicated interstellar probe. Conceived in the 1970s by the British Interplanetary Society, this was not a vague idea but a multi-year engineering study that filled entire volumes with calculations and designs. The mission profile was both simple and monumental: construct a colossal, unmanned spacecraft in the orbit of Earth and send it on a one-way, 50-year voyage to Barnard's star, nearly 6 light-years away. This was a vessel built for one purpose only: to cross the unimaginable gulf between stars and return priceless data from another solar system. The heart of Daedalus was its revolutionary propulsion system, a masterpiece of theoretical engineering. Unlike Orion's brute force atomic pulses, Daedalus relied on the elegance of nuclear fusion. Imagine a complex engine chamber where tiny pellets of frozen fuel, a mix of deuterium and helium-3, are injected at a rate of hundreds per second. These pellets would then be struck by powerful beams of electrons, compressing and heating them to the point of fusion ignition in a microscopic, controlled star. This would create a continuous, controlled fusion reaction, a steady torch of plasma firing out the back of the spacecraft. The sheer scale of this engine was breathtaking, designed to burn for nearly 4 years straight, accelerating the massive probe to a velocity previously only seen in the realm of particle physics, an incredible 12% of the speed of light. At that pace, a journey that would take a chemical rocket tens of thousands of years would be accomplished in a single human lifetime. Daedalus was more than just an engine, however. It was a fully fledged robotic explorer. Its brain was to be an advanced autonomous artificial intelligence, a necessity given that any communication with Earth would take over a decade for a simple round-trip message. This AI would have to navigate the interstellar void, manage the spacecraft systems, and conduct the entire scientific mission on its own. The probe would carry a vast suite of instruments, including large telescopes for planetary observation, spectrometers for analyzing atmospheric compositions, and even a flock of smaller subprobes to be deployed upon arrival for close-range reconnaissance of planets and moons. It was designed to be a complete flyby observatory, giving us our first real-time glimpse of another star's family of worlds. But why was this magnificent concept ultimately shelved? The challenges were as immense as the ambition. The first was the fuel itself. While deuterium is relatively common, helium-3 is extraordinarily rare on Earth. To acquire the vast quantities needed for the mission, the Daedalus team proposed a staggering industrial operation, mining the atmosphere of Jupiter. This would involve creating a whole new infrastructure of robotic mining craft operating in the intense radiation belts of the solar system's largest planet, a feat that remains far beyond our capabilities even today. Beyond the fuel, the engineering required for the engine itself, the precision pellet injection, the powerful electron beams, the containment of the continuous fusion reactions pushed the very limits of known materials science. Daedalus proved that the physics of interstellar travel was sound, but it also highlighted a chasm of technological development that we are still working to bridge. It stands not as a failure, but as a beacon, a detailed map left by one generation of dreamers for the next to follow. This vision of harvesting resources from other worlds to power our ambitions would inspire an even more colossal launch vehicle, one designed to conquer the economics of space itself. Just when you thought the audacity of space engineering couldn't get any grander, along came a concept that made every other rocket look like a toy. If Orion was a city ship and Daedalus a scientific marvel, the Sea Dragon was the ultimate titan of raw power, a leviathan designed not for finesse, but for overwhelming, earth-shaking capability. Conceived in 1962 by the brilliant engineer Robert Truax for the company Aerojet, the Sea Dragon was a super-heavy lift launch vehicle of almost mythical proportions. Its primary mission was breathtakingly simple: to make access to space so cheap and routine that building massive space stations and launching interstellar probes would become matters of logistics, not of national effort. The key to this revolution was a philosophy of radical simplicity and immense scale. While modern rockets are painstakingly assembled in pristine clean rooms, the Sea Dragon was designed to be built in a shipyard, much like a submarine or a massive oil tanker. This approach leveraged existing maritime industrial expertise to slash costs, imagining a future where spaceships were produced with the same efficiency as seafaring vessels. The numbers associated with the Sea Dragon are still staggering, even by today's standards. Picture a rocket standing over 150 meters tall. That's significantly taller than the entire Saturn V Moon rocket. Its first stage alone would have been a colossal 23 meters in diameter, a vast steel-skinned giant. But the most jaw-dropping statistic was its payload capacity: 550 metric tons to low Earth orbit. To put that in perspective, that is more mass than the entire initial structure of the International Space Station, launched in a single flight. You could load an entire space station module, a fleet of satellites, and years of supplies onto one Sea Dragon and send it all up at once. This wasn't just a rocket, it was a freight train to the cosmos, intended to single-handedly create the infrastructure for a true spacefaring civilization by making the cost of getting there almost negligible. Its launch sequence was as dramatic and unorthodox as its design. The completed rocket would be towed horizontally out to sea, far from populated areas. Once at the launch site, the massive vehicle would be flooded with ballast water, causing it to flip upright and float vertically in the ocean, stabilized by its immense lower stage. There would be no complex launch tower, no delicate gantries. Instead, ignition would be a spectacle of pure elemental force. Seawater would be pumped into the base of the rocket's engine bell, and the ignition of the massive first stage engine would instantly flash that water into superheated steam, creating a colossal bubble that would thrust the entire vehicle out of the ocean and into the sky. It was a launch method born of brute force physics, a steam cannon on a scale never before imagined. Furthermore, the Sea Dragon was designed with reusability in mind. After separation, the enormous first stage would simply splash down into the ocean, where it would be recovered by waiting ships, towed back to port, refueled, and prepared for its next journey. This vision of a simple, reusable, ocean-launched giant was poised to completely redefine our relationship with space. So why did this titan of the space age never roar to life? The downfall of the Sea Dragon wasn't a technical failure or a catastrophic test. It was a simple, cold matter of priorities and practicality. By the mid-1960s, NASA budget and entire national focus were overwhelmingly directed toward a single, unambiguous goal: beating the Soviet Union to the moon with the Apollo program. The Saturn V rocket, while a magnificent achievement, was a bespoke, handcrafted masterpiece designed for a specific mission. The Sea Dragon, in contrast, was a general-purpose heavy hauler for a future that hadn't yet arrived. There was simply no immediate mission that demanded its unprecedented lift capacity. Building the industrial infrastructure to construct and launch it would have required a massive investment at a time when space funding was already stretched thin. The project was quietly shelved, a victim of its OWN Chinese letter vision. The dream of outrageously affordable, massive access to space was deferred for decades, its blueprints filed away as a fascinating what-if. Yet the quest for powerful, cost-effective launch systems refused to die, evolving next into a pursuit not of sheer size, but of elegant, runway-to-orbit efficiency. After the era of colossal rockets and interstellar probes came a vision of something far more elegant and accessible, a true spaceship that could operate with the routine convenience of an airliner. This was the dream of single-stage-to-orbit flight, or STO, and its most ambitious champion in the 1990s was a design known as Project Valkyrie. Envision a vehicle that doesn't require massive launch pads or disposable booster stages. Instead, picture a sleek, winged craft taxiing onto a runway, its engines spooling up for a horizontal takeoff. It would climb through the atmosphere under its own power, accelerate directly into orbit to deploy satellites or deliver cargo, then re-enter the atmosphere and glide back to a graceful, unpowered landing on that very same runway. This was the operational fantasy that Valkyrie promised to make real, a vehicle that would transform space from a remote frontier into a routine destination. The key to making this fantasy feasible lay in two critical technological innovations. The first was its revolutionary propulsion system, the linear aerospike engine. Unlike traditional rocket engines with their bell-shaped nozzles, which are optimized for a specific atmospheric pressure, the aerospike was a shape-shifter. It featured a wedge-shaped protrusion with combustion occurring along its sides, and the ambient air pressure itself would naturally form the missing wall of the nozzle. This meant the engine was inherently efficient from sea level all the way to the vacuum of space, providing optimal thrust throughout the entire ascent. It was the perfect engine for a vehicle that had to operate as both a jet and a rocket. The second innovation was in its bones and skin. Valkyrie's airframe was to be constructed from advanced lightweight composites and new metallic alloys, materials that were strong enough to handle the stresses of launch and re-entry yet light enough to meet the brutal, unforgiving math of ESTO. In rocketry, every single kilogram saved in structure is a kilogram that can be dedicated to payload or fuel, and Valkyrie's designers fought a relentless war against mass. The potential payoff for conquering these challenges was nothing short of a second space revolution. By being fully and rapidly reusable, with a turnaround time envisioned in days rather than months or years, Valkyrie promised to demolish the cost of reaching orbit. Estimates suggested it could reduce the price per pound by a factor of 100 or more, effectively turning a billion-dollar launch into a matter of millions. This wasn't just about making government missions cheaper, it was about unlocking the door for true commercial and private enterprise in space. Imagine manufacturing facilities in microgravity, private space stations for tourism, and on-demand satellite deployment becoming as routine as overnight freight. Valkyrie was designed to be the truck, the train, and the airplane for this new space-based economy, a true workhorse for the high frontier. Yet, despite the brilliant engineering and the compelling vision, Project Valkyrie, like so many ESTO concepts before it, ultimately remained a set of blueprints. The fundamental obstacle was the tyranny of the rocket equation, a brutal principle of physics that dictates the exponential relationship between a rocket's mass, its fuel, and its final velocity. For an ESTO vehicle, the margins are excruciatingly thin. The vehicle must carry not only its payload and fuel, but also the engines, wings, thermal protection tiles, and landing gear needed for the entire round trip. The advanced composites and alloys of the 1990s, while impressive, were simply not light enough or strong enough to build a vehicle that could carry a meaningful payload to orbit without becoming impossibly large and heavy itself. The linear aerospike engine, though theoretically superior, was also a complex and undeveloped technology, facing its own significant hurdles in cooling and combustion stability. In the end, the concept was shelved because the technological maturity of the era could not quite catch up to the ambition of the design. The dream of a runway-to-orbit vehicle, however, did not die with Valkyrie. It simply passed the torch, inspiring a new generation of engineers and billionaire entrepreneurs to take up the challenge with fresh ideas and deeper pockets. From the sleek, runway-bound ambitions of the Valkyrie, we now shift our gaze to a vision of a far grander and more enduring voyage. Picture a vessel not designed for quick trips to orbit, but as a permanent home for humanity, a world in its own right embarking on a journey that would span lifetimes. Imagine a colossal cylinder over 600 meters long, gliding silently through the interstellar void. At its core, a massive, gleaming sphere of frozen deuterium ice serves as both its fuel reservoir and its primary propulsion source. This was the Innsman Starship, a concept proposed in the 1960s by Dr. Robert Innsman that fully embraced the idea of the generation ship, a self-contained ark carrying a community of 200 people on a one-way trip to the stars. It was a design that traded the explosive power of an Orion or the high-tech finesse of a Daedalus for something more profound: sustainability and long-term habitability. The architecture of the Innsman Starship was a masterpiece of modular, functional design, created to sustain human life for centuries. The long cylindrical spine of the vessel would house the crew's living quarters, scientific laboratories, and extensive agricultural bays. To combat the debilitating effects of zero gravity on such a long journey, large sections of the ship were designed to rotate, creating artificial gravity through centrifugal force. This would allow for relatively normal daily life. People could walk, plants could grow in soil, and water would flow in a familiar manner. the ship was conceived as a closed ecosystem, a tiny, fragile bubble of Earth's biosphere meticulously engineered to recycle air, water, and waste. It wasn't just a spacecraft, it was a mobile village, a traveling fragment of humanity with its own culture, history, and future unfolding against a backdrop of alien suns and nebulas. The crew would be born, live, and die aboard the ship, with their children and grandchildren inheriting the mission, their ultimate goal being to arrive at a distant, habitable world and seed a new branch of human civilization. Propelling this behemoth across the light years was a system as elegant as it was ambitious. The enormous deuterium ice ball at the front of the ship was its fuel tank, a vast reservoir of potential energy. The propulsion method was a form of pulsed fusion, not entirely dissimilar from the Orion concept but far more controlled. Small portions of this deuterium fuel would be methodically extracted and used in controlled fusion reactions, creating a steady, continuous thrust. While this wouldn't provide the blistering acceleration of some other theoretical drives, it would be incredibly efficient, slowly and steadily building up to a cruising speed that could carry the ship to a nearby star system like Proxima Centauri within a few hundred years. This was a ship built for patience, for the long arc of history, embodying a commitment to interstellar exploration that transcended individual human lifespans. It captured a romantic, almost epic vision of our cosmic destiny, where the journey itself was as important as the destination. The reason the Innsman Starship remains a beautiful blueprint rather than a ship under construction is the same fundamental challenge that has stalled so many grand visions of the future: the mastery of fusion power. The concept relies entirely on a compact, reliable, and controllable fusion reactor technology that, despite decades of research, remains just beyond our grasp. We can create fusion reactions, as in hydrogen bombs, but we cannot yet sustain and harness them for the steady, dependable thrust required for a centuries-long voyage. Furthermore, the immense biological and sociological challenges of a multi-generational space journey present another layer of profound difficulty. How does a society remain stable and healthy when isolated for hundreds of years? How do you prevent genetic stagnation? These were questions the Innsman design acknowledged but could not fully solve with 1960s knowledge. It was shelved because it was a concept that demanded a technological and sociological revolution that has yet to occur. Its true legacy lies in its powerful reimagining of the spacecraft not as a mere vehicle, but as a home, a theme that resonates deeply with our next concept, which asked an even more fundamental question. Before we build ships to travel between stars, how do we learn to build permanent homes in the void of space itself? Before we can even dream of sending generation ships to other stars, we first have to answer a far more fundamental question. How does humanity learn to live, not just visit, in the void of space? How do we create a home where none has ever existed? This challenge led to some of the most breathtaking architectural concepts ever conceived, blueprints for entire worlds built from scratch. Among the most iconic and influential of these was the Bernal sphere, a space habitat that redefined the very idea of a colony. It wasn't a cramped station or a utilitarian outpost. It was designed to be a true home for thousands, a self-contained biosphere floating in the solar system. The origins of this idea stretch all the way back to 1929, when the visionary physicist John Desmond Bernal first proposed a spherical habitat as a place for humanity to thrive beyond Earth. But it was decades later, in NASA's landmark 1975 summer study, that this concept was fleshed out with serious engineering detail, capturing the public's imagination and setting a bold standard for what our future in space could look like. Stepping inside a completed Bernal sphere would be an experience unlike any other on Earth. the entire structure, a sphere roughly 1 mile across, would be rotating steadily. This rotation uses centrifugal force to create artificial gravity, but with a profound difference from Earth. The gravity would only exist on the inner surface of the sphere's shell. So, if you were standing inside this vast world, the ground would curve upward all around you, arching over your head until it met at the opposite end of the sphere. You would literally be living on the inside of a giant ball, with the entire landscape, towns, forests, and lakes wrapped around you. The sensation would be like standing at the bottom of a colossal, planet-sized bowl. To provide light and simulate a natural day-night cycle, enormous external mirrors would be positioned to reflect sunlight into the sphere through large windows. These mirrors could be angled to create sunrise and sunset, and even blocked to simulate night, allowing the 10,000 residents to live by a familiar 24-hour rhythm. The interior environment was envisioned as a lush, park-like setting, complete with rivers, villages, and carefully managed woodlands, all contained within a breathable atmosphere under a controlled climate. It was the ultimate expression of bringing a piece of Earth into space, a fully engineered ecosystem designed for long-term human flourishing. The NASA studies that developed this concept were not mere science fiction. They were rigorous exercises in systems engineering. Teams of scientists and engineers calculated everything from the structural integrity of the sphere's hull to the complex balance of its closed-loop life support system. They worked out how to grow food in space-based agriculture modules, how to recycle every drop of water and every molecule of air, and how to manage waste in a system with no external environment to absorb it. These detailed plans proved a revolutionary point. From a purely physics and engineering perspective, building large-scale, permanent space colonies was theoretically possible. There was no law of nature that said it couldn't be done. The Bernal sphere and its cylindrical cousins like the O'Neill cylinder moved the goalposts from if we could build space cities to how we might one day build them. They provided a tangible target for a future where humanity is a multi-planetary species, no longer confined to our single, fragile world. Yet, for all its inspirational power and theoretical soundness, the Bernal sphere concept was ultimately shelved, and the reason boils down to one immense, grindingly practical problem: the astronomical cost and sheer physical difficulty of getting all the materials into space. Constructing a habitat 1 mile in diameter, capable of supporting thousands of people, would require millions upon millions of tons of steel, aluminum, glass, soil, and water. In the 1970s, and still largely today, every single kilogram of that material would have to be launched from the surface of Earth at a cost of thousands, or even tens of thousands of dollars per kilogram. The energy and financial resources required would dwarf the entire Apollo program, representing a multi-trillion-dollar undertaking that no single government or entity was willing to fund. Furthermore, the assembly of such a colossal structure in orbit presented a staggering set of construction challenges that were far beyond the capabilities of the space shuttle era. The dream was grounded not by a failure of imagination, but by the brutal economics of Earth's gravity well. The Bernal sphere forced a generation of engineers to confront a critical truth. If we are ever to build such cosmic cities, we cannot rely on shipping everything from Earth. We must learn to use the resources we find out there, a realization that would push the next wave of visionaries to think on an even grander, more resourceful scale. Now, let's dive into a concept that is perhaps the most elegant and self-sufficient Starship idea ever conceived: the Bussard Ramjet. Envision a vessel that solves the single greatest problem of interstellar travel: the need to carry colossal amounts of fuel by simply harvesting what's already out there. First proposed by physicist Robert W. Bussard in 1960, this brilliant idea suggested a spacecraft could act like a cosmic whale, swimming through the galactic ocean and filtering its fuel from the thin soup of interstellar space. The principle is breathtakingly simple in theory. Instead of launching with a finite supply of propellant, the ship would deploy an immense magnetic field, a kind of invisible net stretching thousands of kilometers across. This colossal magnetic scoop would sweep up the lone hydrogen atoms that drift through the void, the most abundant element in the universe. Those captured atoms would then be channeled into an onboard fusion reactor, where they would be fused together, and the resulting energy would be expelled as a powerful exhaust jet, providing continuous, relentless thrust. This creates a beautiful, closed-loop system. The faster the ship goes, the more hydrogen it rams into its collector, and the more thrust it can generate, theoretically allowing it to accelerate almost indefinitely. It promised a vessel of pure potential, capable of reaching a significant fraction of the speed of light, untethered from the need for pre-packed fuel, and free to roam the galaxy. The sheer genius of this concept captured the imagination of scientists and science fiction writers alike, most famously in Powell Anderson's novel, Tau Zero, where a runaway Bussard Ramjet becomes a vessel carrying its crew through the end of the universe. It represented the ultimate expression of freedom in space exploration, a ship that could, in principle, travel forever. The engineering, however, was where the dream collided with formidable reality. Creating a magnetic field large enough to be effective was one thing, but the real magic was supposed to happen in the fusion reactor. The reactor would need to be capable of fusing the collected hydrogen protons, the most common type of hydrogen, in a process known as proton-proton fusion. This is the same reaction that powers our Sun, but it is incredibly slow and difficult to initiate, requiring temperatures and pressures far beyond what was considered practical for a compact spaceship engine. Some designs suggested a workaround, focusing on regions of space richer in deuterium, but that undermined the core premise of using universally available fuel. The ramjet was a solution predicated on a technology-efficient, compact proton fusion that remains one of the holy grails of physics today. Unfortunately, an even more fundamental flaw was later uncovered through rigorous analysis. While the magnetic scoop was intended to gather fuel, it would also create immense drag as it plowed through the interstellar medium at high speeds. Think of it like trying to run through a swimming pool while holding a giant butterfly net. The resistance of the water against the net would slow you down far more than any benefit you might gain. Physicists calculated that in the vast regions of interstellar space the ramjet was designed to traverse, the density of hydrogen is so incredibly low that the thrust generated from fusing the collected atoms would be negligible. Meanwhile, the drag force on the magnetic field structure itself would be substantial, effectively acting as a brake on the spacecraft. For the Bussard Ramjet to work as intended, the interstellar medium would need to be hundreds or even thousands of times denser than it actually is in most parts of our galaxy. This harsh reality, a sobering lesson in the actual conditions of deep space, ultimately led to the concept being shelved as a practical means of propulsion. It was a magnificent idea slain by the cold, hard numbers of physics, a reminder that the universe does not always conform to our most elegant solutions. Yet, this setback did not extinguish the quest for fuel-efficient starflight. It simply forced visionaries to look for propulsion in even more exotic and unexpected places. While the Bifrost lunar space elevator may sound like pure science fiction, the physics behind it is surprisingly grounded. The concept leverages one of the Moon's greatest advantages for large-scale construction, its significantly weaker gravity. Earth's powerful gravitational pull is the primary reason building a space elevator here remains an immense challenge. demanding a material with near-mythical strength, like carbon nanotubes that we can't yet produce in sufficient quantities. The Moon, however, with only 1/6 of Earth's gravity, completely changes the equation. The tension on a cable dangling from lunar orbit is dramatically lower, meaning we could theoretically build a functional lunar elevator right now using existing high-strength materials like Kevlar or Xylon. This isn't a far-off dream waiting for a materials science revolution. It's a project that, from a pure physics standpoint, is within our grasp. The operational brilliance of Bifrost lies in its location and its purpose. The cable wouldn't just dangle aimlessly into space. It would be anchored to the lunar surface and extend tens of thousands of kilometers outward, reaching a special point in space known as the Earth-Moon Lagrange Point 1. This is a gravitational sweet spot where the pulls of Earth and the Moon balance each other, allowing an object to remain in a stable position relative to both bodies. From this far end of the cable, the centrifugal force from the Moon's rotation would pull outward, perfectly counteracting the Moon's gravity pulling inward, keeping the entire structure taut and stable. Along this impossibly long ribbon, automated climbers, essentially robotic freight elevators, would travel up and down, powered not by rocket fuel but by electricity, likely beamed wirelessly via lasers or solar power. These climbers would carry lunar resources like water ice from permanently shadowed craters or rare earth metals mined from the surface, delivering them to a waiting station at the top. From there, this raw material could be shipped throughout cislunar space with minimal energy, fueling everything from space stations to interplanetary missions. Bifrost would transform the Moon from a distant destination into the central hub of a true space-based economy, the foundational port for all traffic in the inner solar system. So why does this elegant, feasible idea remain a set of blueprints in a drawer? The answer is not a single catastrophic flaw, but a classic chicken and egg problem of cosmic proportions. The initial investment to build Bifrost would be astronomical, requiring a sustained multi-billion-dollar commitment over many years before the first climber ever carried a single kilogram of payload. This investment would need to come at a time when there is not yet a large-scale, profitable lunar industry to justify it. We can't build the elevator until we have a thriving lunar economy to use it, and it's incredibly difficult to build that economy without the cheap transportation the elevator would provide. Furthermore, constructing Bifrost would itself require a massive pre-existing industrial presence on the Moon to manufacture and deploy the cable and its components, another infrastructure that doesn't yet exist. The project was shelved not because it was impossible, but because it was a visionary leap that arrived before its economic time. It awaits a future where humanity's commitment to the Moon is permanent and industrial in scale, a future where building permanent, reusable infrastructure is the clear next step. This grand vision of building not just vehicles but lasting architectural works in space sets the stage perfectly for our next concept, which takes the idea of a permanent habitat and scales it up to an entire world. Building on the breathtaking ambition of the Bernal sphere, physicist Gerard K. O'Neill and his students at Princeton University took the concept of a space habitat and transformed it into a detailed, tangible vision for millions to call home. His iconic O'Neill cylinder, designed in the 1970s, remains one of the most powerful and enduring images of humanity's future in space. Imagine not a single sphere, but a pair of massive cylinders, each one an astonishing 20 miles long and 5 miles in diameter, rotating in opposite directions to cancel out gyroscopic effects and maintain a stable orientation. Paired together like two colossal soda cans end to end, these structures would provide an interior land area equivalent to a large, bustling city on Earth, all contained within a carefully engineered shell floating in the void. This was not conceived as a mere outpost or a scientific station. It was a blueprint for a new branch of human civilization, a place for millions to live, work, and thrive entirely independent of our home planet. The experience of life inside an O'Neill cylinder would be nothing short of surreal and magnificent. The entire inner surface of each cylinder would be a vast, landscaped environment, with alternating strips of land and long, transparent windows running the entire length of the structure. Because the cylinder is spinning to create artificial gravity, the force would push everything outward toward the shell. This means you would stand on the inner curved surface, with the ground arching up on either side of you until it met overhead, creating a stunning, enclosed valley that stretched to the horizon in both directions. Overhead, 3 enormous, rectangular mirrors would be hinged to the stationary central axis of the cylinder. These mirrors would be angled to reflect sunlight through the windows, bathing the interior in a brilliant, natural glow. By slowly adjusting these mirrors, the colony could simulate a perfect 24-hour day-night cycle, with the light dimming for a peaceful evening and brightening for a new dawn. The landscape itself could be sculpted to contain rolling hills, forests, rivers, and lakes, with towns and communities dotting the countryside. The weather could even be managed, creating gentle rains and predictable seasons within this fully controlled, sealed world. It was a vision of space colonization that was not about survival in a hostile environment, but about creating a new, perhaps even improved, version of earthly life. The propulsion behind the O'Neill cylinder was not engines, but an ideological movement. O'Neill's work, popularized in his seminal book, The High Frontier, became the scientific and philosophical cornerstone of the space colonization movement. He argued that building these massive habitats was not just a fanciful dream, but a logical and necessary step for the long-term survival and expansion of humanity. Free from the constraints of a planetary gravity well, these colonies could be powered by limitless, clean solar energy, beaming it in from space. They could develop their own unique cultures, political systems, and economies, potentially solving many of the resource and environmental problems that plague Earth. The cylinders were presented as a positive, hopeful future, a way to open the high frontier of space for the benefit of all humankind. This powerful vision captured the public imagination in the 1970s, inspiring a generation of engineers, scientists, and enthusiasts to believe that a future among the stars was not only possible but inevitable. Yet, for all its inspirational power and rigorous engineering backing, the O'Neill cylinder, like the Bernal sphere before it, was ultimately shelved. The primary obstacle was, once again, the staggering scale of the undertaking and the astronomical cost associated with it. Constructing just one of these 20-mile-long cylinders would require millions of tons of raw materials, metals, glass, soil, and water. In the 1970s, and still today, the only conceivable source for that volume of material was the Earth itself. Launching it all from our planet's deep gravity well using conventional rockets would have been financially ruinous, costing many trillions of dollars and requiring launch rates thousands of times greater than anything humanity has ever achieved. The sheer magnitude of the construction project in orbit was also far beyond the capabilities of the fledgling Space Shuttle program. The vision was grounded by the brutal reality of Earth's gravity and the limitations of contemporary industrial spaceflight. The O'Neill cylinder forced a critical realization. If we are ever to build such immense structures, we cannot be tethered to Earth for our supplies. We must learn to live off the land, to use the resources readily available in space itself. This fundamental insight, born from the shelving of O'Neill's dream, would directly inspire the next wave of concepts which sought not just to build in space but to power the Earth from it. Imagine a power source so reliable it never experiences night, never suffers a cloudy day and operates completely free of the carbon emissions driving climate change. This is the extraordinary promise that the SPS Alpha solar power satellite concept offered, a vision of solving our planet's energy crisis not by looking down at the ground, but by looking up to the limitless resources of space itself. The name itself, Solar Power Satellite via Arbitrarily Large Phased Array, reveals the core of its revolutionary design. Unlike a traditional monolithic satellite, SPS Alpha was conceived as a vast, flower-like structure composed of tens of thousands of small, identical, and incredibly lightweight components. Picture a sprawling constellation of thin film mirrors and microwave transmitters, all working in perfect harmony, assembled not by astronauts in bulky suits, but by a swarm of autonomous robots in the zero-gravity environment of high Earth orbit. This modular approach was a masterstroke, moving away from the idea of building one perfect, fragile machine and instead embracing a philosophy of scalable, resilient space architecture. If one small module failed, the rest of the system could simply compensate, making the entire power station incredibly robust and repairable. The operational principle of this orbital power plant is a breathtaking feat of engineering. In the pristine vacuum of space, unfiltered by Earth's atmosphere, sunlight is far more intense and available over 99% of the time. The satellite's vast array of mirrors would focus this raw solar energy onto high-efficiency photovoltaic panels, converting it into electricity. But here's the real genius. Instead of trying to run a massive cable down to Earth, the satellite would then transform that electricity into a low-density microwave beam. Think of it not as a dangerous laser, but more like a highly focused version of the wireless energy transfer used to charge your electric toothbrush, just on a planetary scale. This microwave beam would be precisely targeted at a receiving station on the Earth's surface, a sprawling array of antennas known as a rectenna, which would be located in a remote, unpopulated area. The rectenna would safely convert the microwaves back into electricity and feed it directly into the global power grid. The result would be a constant, predictable flow of base load power, day and night, through rain and shine, providing a foundational energy source that could finally displace fossil fuels on a massive scale. The potential benefits of such a system are almost incalculable. A single, large SPS Alpha satellite could generate multiple gigawatts of power, equivalent to several large nuclear power plants, but without any of the radioactive waste or fuel requirements. Deploying a fleet of them could theoretically meet the entire energy demands of major nations, offering a clear path to a post-carbon global economy. Furthermore, by providing a reliable and potentially cheap source of electricity, it could uplift developing nations, power massive water desalination plants, and even provide the energy needed for direct air capture technologies to remove existing carbon dioxide from the atmosphere. It represented the ultimate expression of using space technology for direct, tangible benefit to all of humanity. A clean energy revolution launched from the ultimate high ground. So why is this seemingly perfect solution still a concept in a research paper and not a reality under construction? The reasons for its shelving are as massive as the project itself. First, there were significant technical and public perception hurdles regarding the microwave beam. While scientists demonstrated that the beam's intensity could be kept at safe levels, you could theoretically walk through the rectenna field without harm. The public and many policymakers harbored deep-seated fears about death rays from space and the potential ecological impact on birds or atmospheric conditions. Second, the efficiency of the entire process, from sunlight to electricity to microwave and back to electricity, involved multiple energy conversion steps, each with its own losses. While the math worked on paper, building a system that could compete economically with ever-cheaper terrestrial solar and wind power was a monumental challenge. But the single greatest obstacle was, and remains, the astronomical initial investment. Launching the thousands of modules and robotic assemblers required to build the first SPS Alpha would require hundreds, if not thousands, of rocket launches, representing a project cost estimated in the hundreds of billions of dollars. No single government or private entity has been willing to take on that level of financial risk for an unproven technology, despite the potential for long-term payoff. The project was shelved not because it was a bad idea, but because it was an idea so grand it demanded a level of international cooperation and financial commitment that the world has yet to muster. The ambition to harness the environment of space to protect our own planet, however, is a powerful driver that connects directly to another concept born from a desire to use cosmic technology for earthly salvation. From the grand vision of beaming clean energy from orbit, we pivot to a far more urgent and sobering concept, one born not from ambition but from self-preservation. Picture a scenario astronomers know is not a matter of if, but when, a sizable asteroid is discovered on a direct collision course with our planet. In the 1960s, a group of brilliant students at the Massachusetts Institute of Technology took this terrifying hypothetical and turned it into one of the most vital academic exercises in history. Their mission, dubbed Project Icarus, was a direct response to a challenge from NASA: design a realistic spacecraft capable of intercepting and deflecting a doomsday asteroid. The specific threat they were given was a fictional version of the real near-Earth asteroid Icarus, imagined to be on an impact trajectory after a close encounter with the Sun. The clock was ticking, and their task was to devise a plan to save the world. The design these students produced was as pragmatic as it was audacious, a testament to Cold War-era thinking applied to a cosmic problem. Their proposed spacecraft was a robust interplanetary vehicle, launched by a Saturn V rocket, carrying a payload of nuclear warheads. The strategy was not to shatter the asteroid into pieces, which could simply create multiple, smaller impactors, but to use the carefully timed force of nuclear detonations to nudge it off course. The concept relies on a principle known as momentum transfer. By detonating the warheads at a precise standoff distance from the asteroid's surface, the explosion would vaporize a layer of rock, creating a jet of superheated material blasting away. The reactive force from this jet would act like a natural rocket engine, ever so slightly altering the asteroid's velocity. Over the millions of miles of its remaining journey, that tiny change in speed would be enough to make it miss Earth entirely. It was a plan that required pinpoint navigation, flawless timing, and a deep understanding of orbital mechanics, proving that in the face of extinction-level threats, humanity's most powerful weapons could potentially be used as its most precise tools. Project Icarus was far more than a classroom assignment. It was a foundational proof of concept for the entire field of planetary defense. It demonstrated, with rigorous engineering and physics, that humanity possessed the theoretical capability to defend itself from a primordial cosmic threat. For the first time, the idea of asteroid deflection moved from the pages of science fiction into the realm of serious scientific study. The project forced a confrontation with the immense logistical and political challenges of such a mission. It underscored the absolute necessity of early detection. You cannot deflect an asteroid you don't see coming until it is too late. This highlighted the critical need for dedicated sky survey telescopes, a legacy that continues today with programs like NAS, a Planetary Defense Coordination Office. Furthermore, the project brought the complex issue of using nuclear weapons in space to the forefront. The political and ethical ramifications of deploying such devices, even for a peaceful purpose, were immense, involving international treaties and global fears about the militarization of space. The students' work made it clear that saving the planet would require not just scientific and engineering prowess, but unprecedented global cooperation and diplomacy. Ultimately, Project Icarus was shelved as an actual mission for the best reason possible. No imminent civilization-ending asteroid threat has been discovered. It remains a brilliant academic study, a fire drill that prepared our planetary emergency services for a disaster that has not yet come. Its legacy, however, is profoundly alive. The strategies and principles developed by those MIT students directly influenced later research and mission concepts, from the kinetic impactor approach demonstrated by NASA, a recent DART mission, to ongoing studies of gravity tractors and ion beam shepherds. The project serves as a permanent reminder of our vulnerability in a cosmic shooting gallery, and a powerful declaration that we do not have to be passive victims of celestial mechanics. This sobering reality of planetary defense, born from the tensions of the Cold War and the universal fear of annihilation, naturally leads us to examine another technology that emerged from the crucible of global conflict, one with a far more terrestrial and contentious purpose. While the United States was meticulously refining the lunar module for its historic Apollo missions, a radically different and far more imposing spacecraft was taking shape on Soviet drawing boards. This was the UR-700M, a lunar lander of such staggering proportions it embodied the Soviet philosophy of achieving spaceflight through sheer, unadulterated power. Where the American approach was one of elegant, weight-conscious precision, the Soviet answer was a behemoth, a vehicle designed not for finesse, but for a direct, brute force conquest of the Moon. The entire mission architecture was built around a concept known as direct ascent, a method NASA had considered and deliberately rejected. In this daring scenario, a single, integrated spacecraft would launch from Earth, fly directly to the Moon, land in its entirety, and then blast off from the lunar surface to make the return journey straight back to Earth. This eliminated the need for the complex orbital rendezvous and docking maneuvers that were central to the Apollo mission profile, but it came at an immense cost. The lander had to be enormous. It needed to carry all the fuel and propulsion systems for both the descent and the entire ascent back to Earth, making it a true monster of engineering. The proposed UR-700M lander was a vehicle that would have utterly dwarfed the spidery, fragile-looking Apollo lunar module. Imagine not a delicate two-stage craft built for two, but a colossal multi-stage behemoth, a virtual skyscraper standing on the lunar surface. It was designed to be launched by the similarly monstrous UR-700 rocket, a design from the brilliant but controversial chief designer Vladimir Chelomey. This rocket itself was a titan, conceived to outperform even the troubled Soviet N-1 rocket, with a cluster of powerful engines intended to hurl its massive payload on a direct trajectory to the Moon. The lander's scale was a direct result of its mission profile. It had to be a self-contained interstellar express, carrying a robust descent stage, a powerful ascent stage, and all the life support and systems needed for a cosmonaut to journey to the Moon, land, and return without any help from a separate command module waiting in orbit. Seeing this monolithic Soviet lander standing next to the Apollo LM would have been like comparing a main battle tank to a dune buggy. It was a physical manifestation of a completely different engineering ideology, one that favored overwhelming force over meticulous optimization. This colossal undertaking, however, was ultimately doomed by a combination of technical misfortune and shifting political fortunes. The UR-700M project was inextricably linked to the fate of its delivery vehicle, the UR-700 rocket, which itself was in a fierce internal competition with Sergei Korolev's N-1 rocket. While the N1 suffered a series of catastrophic launch failures, the UR-700 never even made it to the launch pad. The sheer complexity and cost of developing such a gargantuan system stretched the Soviet space program's resources to their limits. Then, in July of 1969, the defining event of the space race occurred. Apollo 11's Eagle lander touched down on the Sea of Tranquility. The American flag was planted, and the Soviet lunar dream was effectively shattered. With the geopolitical prize won by their rivals, the impetus for funding the astronomically expensive UR-700M and its rocket evaporated almost overnight. The project was abruptly cancelled, joining the N1 as a monument to a lost lunar campaign. The legacy of the UR-700M is one of the most captivating what-if scenarios in the history of space exploration. Had the Soviet political and engineering bureaucracy been more unified, or had the N1 succeeded earlier, the UR-700M could have very well been the spacecraft that carried a cosmonaut to the moon. This would have dramatically altered the narrative of the space race, potentially creating a scenario where the two superpowers both achieved a lunar landing, but through fundamentally different and competing technological paths. The sight of a massive, utilitarian Soviet lander on the moon would have presented a stark contrast to the American achievement, shaping the aesthetic and ideological perception of space exploration for decades to come. The sheer ambition of the direct ascent method, while ultimately shelved, continues to inform modern design thinking, particularly as we look toward missions to Mars, where different mission architectures are still being fiercely debated. The story of the UR-700M is a powerful reminder that history is not a single, inevitable path, but a tapestry woven from the threads of competing ideas, brilliant minds, and sometimes the simple, crushing weight of reality. In the wake of the Space Shuttle era, NASA yearned for a successor that would finally crack the code on affordable, routine space access. The answer seemed to arrive in the sleek, futuristic form of the X-33, a dazzling half-scale technology demonstrator for a visionary spacecraft known as the Venture Star. This wasn't just an incremental upgrade, it was a radical leap designed to be the anti-shuttle. Where the shuttle was a complex, expensive patchwork of reusable orbiter, disposable boosters, and a giant fuel tank, the Venture Star was conceived as a pure, single stage-to-orbit vehicle. Its mission was to launch vertically like a rocket, deliver its payload to space, and then return to Earth, gliding back to a graceful, horizontal landing on a standard runway, ready to be refueled and flown again within days. The promise was a reduction in launch costs from around $10,000 per pound to a mere $1,000, a revolution that would have flung the doors to space wide open for commerce, science, and tourism. The public and media excitement in the late 1990s was electric, fueled by stunning animations of the angular, silver spacecraft that looked like it had flown straight out of a science fiction blockbuster. The magic behind this audacious promise lay in two groundbreaking technologies. The first was its radical lifting body design. Unlike conventional aircraft that need wings for lift, the Venture Star's entire body was shaped to generate lift as it sliced through the atmosphere during re-entry. This elegant design eliminated the need for heavy, disposable wings, saving immense weight and complexity. It was essentially a flying wing in the shape of a spacecraft, a concept that looked incredibly sleek but demanded a mastery of aerodynamics that pushed the boundaries of computational fluid dynamics. The second, and even more critical innovation, was its propulsion system. The Venture Star was to be powered by a ring of revolutionary linear aerospike engines. Traditional rocket engines have a bell-shaped nozzle that is perfectly tuned for one specific altitude, either the thick air at sea level or the vacuum of space, forcing a compromise in efficiency. The linear aerospike was different. It was essentially a bell nozzle turned inside out, a wedge-shaped protrusion with combustion occurring along its sides. The ambient air pressure itself would naturally form the outer boundary of the exhaust plume, meaning the engine automatically adjusted its efficiency from the launch pad all the way to orbit. This was a monumental advantage, offering the performance of multiple engines in a single, versatile system. This visionary project was structured as a groundbreaking public-private partnership with the aerospace giant Lockheed Martin. The idea was for NASA to share the development costs and risks, fostering a new commercial space industry that would eventually own and operate the Venture Star fleet. The X-33 prototype was the crucial first step, a suborbital test vehicle intended to prove the integrated technologies of the lifting body airframe, the composite fuel tanks, and the aerospike engines in real flight. For a few years, it seemed like the future was being built inside a hangar in Palmdale, California. Then, reality intervened with a series of brutal and ultimately fatal technical challenges. The most formidable of these was the complex composite liquid hydrogen fuel tank. To save every possible kilogram, the tank was not made of traditional aluminum but of lightweight graphite composite, a material similar to that used in high-end tennis rackets or fishing rods, but on an enormous cryogenic scale. This material had to withstand not only the immense forces of launch, but also the extreme cold of the liquid hydrogen fuel at -423 degrees Fahrenheit. During a structural test in late 1999, a critical failure occurred. The composite tank, pressurized with nitrogen gas, ruptured catastrophically. The investigation revealed an insidious flaw. The layers of the composite material had delaminated under stress, a problem that was fundamentally rooted in the material science of the time. Fixing it would have required a complete redesign, adding significant weight and cost, and shattering the delicate mass budget that was the very foundation of the single-stage to orbit dream. The cancellation of the X-33 program in 2001 was a profound disappointment, a stark reminder of the chasm that can exist between visionary design and practical engineering. The failure of the composite tank was the immediate cause, but it also symbolized the immense difficulty of the single-stage to orbit challenge itself. The tyranny of the rocket equation, which dictates that a rocket must carry exponentially more fuel to carry more fuel, leaves almost no margin for error. The Venture Star needed to be a masterpiece of lightweight construction, and the materials of the 1990s simply weren't up to the task. The collapse of the project sent a chilling ripple through the aerospace world, seemingly proving that fully reusable, single-stage spacecraft were a financial and technical bridge too far. For nearly a decade, the field of reusable launch vehicles entered a quiet period, with major players retreating to more conservative, evolutionary designs. The dream of runway-to-orbit spaceflight, which had burned so brightly with the X-33, was shelved, its brilliant promise deferred. Yet, the knowledge gained from its development, particularly in composite structures and the physics of the aerospike engine, was not lost. It became a crucial inheritance, a set of hard-won lessons that would be studied intently by a new wave of private space companies who were just beginning to imagine their own revolutions. This story of reaching for a transformative goal and being halted by the limits of material science finds a powerful parallel in our next concept, which also saw its grand ambitions curtailed by the immense challenges of powering a journey into the deep unknown. Just as the X-33's dream of affordable orbit was grounded by the limits of materials, another equally ambitious project was being conceived to conquer the vast distances beyond Mars, a mission that would have harnessed the atom not for explosive thrust, but for the quiet, relentless power of electricity. In the early 2000s, NASA embarked on a bold new path named Project Prometheus, an initiative aimed at developing nuclear electric propulsion for a new era of deep space exploration. At the heart of this endeavor was its flagship mission, the Jupiter Icy Moons Orbiter, or JIMO, a probe of such capability and scale it would have dwarfed every interplanetary mission that came before it. While previous missions to the outer planets were like swift, resource-limited tourists snapping pictures from a passing bus, JIMO was designed to be a permanent resident, a sophisticated scientific laboratory that could move into the neighborhood of Jupiter's enigmatic moons and study them for years on end. Its primary targets were the icy Galilean satellites Europa, Ganymede, and Callisto worlds that hide vast, global oceans beneath their frozen crusts, making them some of the most compelling places in our entire solar system to search for environments that could harbor life. The key to JIMO's unprecedented mission profile was its revolutionary power and propulsion system. Unlike the traditional chemical rockets or even the small solar panels used by previous outer planet probes, JIMO would be powered by a small, compact nuclear fission reactor. This wasn't a radioactive power source like the plutonium-powered batteries used on missions like Voyager or Cassini, which merely convert the heat from radioactive decay into a few hundred watts of electricity. This was a true uranium-fueled reactor capable of generating a continuous and immense flow of electrical power on the order of hundreds of kilowatts, enough to run a small neighborhood. This abundant electrical bounty was then to be channeled into a highly efficient ion propulsion system. Ion engines work by electrically charging a propellant gas, usually xenon, and accelerating the ions out of the engine using an electric field. They generate only a whisper of thrust, far less than a chemical rocket, but they are incredibly frugal with their fuel and can fire continuously for months or even years. Over time, this constant, gentle push builds up to tremendous speeds, making them perfect for the long hauls and complex orbital maneuvers required in the outer solar system. JIMO ion drive would have allowed it to do something no previous mission could. After arriving at Jupiter, it wouldn't just whip past its targets. Instead, it could slow down, enter orbit around Europa, conduct a detailed survey for months, then fire its engine again to leave Europa's orbit and travel to Ganymede to repeat the process, and then yet again to Callisto. It was designed to be a master of its own destiny in the Jovian system, a movable observatory with the energy and endurance to give us an intimate, long-term look at each of these alien worlds. With this incredible power supply, JIMO's scientific toolkit would have been nothing short of revolutionary. The reactor's electricity would have powered a suite of instruments of a size and capability previously unimaginable for an outer planet mission. It could have carried a powerful ice-penetrating radar capable of mapping the depth and structure of the subsurface oceans on Europa and Ganymede, revealing the thickness of the icy shells and potentially even identifying lakes or structures near the ocean floor. It could have featured massive, high-gain antennas for returning a torrent of data back to Earth, streaming high-resolution video and immense volumes of scientific measurements that would have transformed our understanding. Its cameras could have captured features down to the scale of a school bus on the surfaces of these moons, revealing the complex geology of ice rafts, fissures, and potential cryovolcanoes in stunning detail. Spectrometers could have analyzed the composition of surface ices and any plumes of water vapor erupting into space, searching for complex organic molecules, the building blocks of life. JIMO was more than a mission. It was a paradigm shift, promising to turn these distant, mysterious points of light into richly mapped and deeply understood worlds, and in doing so, answering fundamental questions about the potential for life beyond our own planet. Yet, this magnificent vision for exploring the ocean worlds of Jupiter was ultimately shelved, a casualty of the complex interplay of budget, technical risk, and shifting political winds. The projected cost of the mission ballooned, with estimates soaring well past several $billions, making it a prime target for budget cuts at a time when NASA was being directed to refocus its priorities and funding toward the Constellation program, which aimed to return humans to the Moon and eventually send them to Mars. The technical complexities were also immense. While nuclear reactors had been flown in space before by the Soviet Union, developing a new American-made space reactor that was safe, reliable, and powerful enough for JIMO was a formidable challenge in its own right, requiring years of development and rigorous safety testing. The specter of a launch failure involving a live nuclear reactor also raised significant public and political concerns, despite all the safety protocols that would have been in place. Faced with these towering hurdles, NASA made the difficult decision to cancel Project Prometheus and the JIMO mission in 2005. Its shelving left a profound gap in our exploration of the outer solar system, a missed opportunity that has only recently begun to be addressed by missions like the European Space Agency's JUICE and NASA's own Europa Clipper. While these modern missions are magnificent in their own right, they lack the game-changing power and propulsion that would have allowed JIMO to be a long-term, multi-moon orbiting platform. The promise of nuclear power for peaceful space exploration, however, was not extinguished by JIMO cancellation. It simply found new, more focused avenues of development. Now, let's turn our attention to a propulsion concept that feels like it was pulled straight from the engine room of a starship, a technology that could dramatically shrink our solar system. Meet the VASIMR plasma rocket, which stands for the Variable Specific Impulse Magnetoplasma rocket. While many of the concepts we've discussed relied on brute force or massive scale, VASIMR represents a more refined and intelligent approach to space travel. Imagine an engine with no traditional combustion, no fiery exhaust plume in the conventional sense. Instead, it works by creating a superheated soup of electrically charged gas, known as plasma, and then using magnetic fields to funnel this star-like material out the back at incredible speeds. This isn't science fiction. It's a serious technology that has been championed for decades by former NASA astronaut Franklin Chang Diaz, who famously logged over 1,600 hours in space across 7 shuttle missions, and then dedicated his life to advancing the very technology that could one day carry humans to Mars and beyond. The true beauty of the VASIMR design lies in its sophisticated, multi-stage process. It starts with a neutral gas, typically argon or hydrogen, which is injected into a first-stage chamber. Here, radio waves bombard the gas, stripping electrons from their atoms and turning it into a low-temperature plasma. This shimmering, electrically charged soup is then channeled into a second, more powerful stage, often called the booster. This is the heart of the engine, where a specialized radio frequency heater, similar to the technology in a microwave oven but vastly more powerful, energizes the plasma to temperatures of millions of degrees hotter than the surface of the sun. At these extremes, the plasma would instantly vaporize any physical material it touched. This is where VASIMR genius truly shines. It contains and directs this star in a bottle, not with a solid metal nozzle, but with superconducting magnets that form an invisible, indestructible magnetic nozzle. The plasma trapped within these magnetic fields is then smoothly guided and expelled to produce a steady, efficient thrust. It's a remarkably elegant dance of physics, turning electricity into pure propulsion. This unique method of operation gives VASIMR a key advantage that chemical rockets simply cannot match: variability. A traditional rocket engine is like a car with only one gear. It's either on at full power or it's off. VASIMR, however, is like a car with a full, seamless transmission. It can be tuned for high thrust, which is great for quick maneuvers and getting out of orbit quickly, or it can be dialed back to run in a high-efficiency mode, providing a gentle but constant push for months on end to build up tremendous speed for long interplanetary voyages. This ability to shift its specific impulse, a measure of propulsion efficiency, makes it the ideal engine for a versatile interplanetary tugboat. It could efficiently haul heavy cargo from Earth orbit to a Martian orbit, or be configured for speed to carry astronauts on much faster transits. A journey to Mars that typically takes 6 to 9 months with conventional propulsion could, in theory, be slashed to as little as 40 days with a powerful enough VASIMR engine, drastically reducing the crew's exposure to dangerous cosmic radiation and the physiological deterioration of long-duration spaceflight. So, if this technology is so promising, why isn't it already ferrying cargo between planets? The critical challenge isn't the engine itself. A working prototype called the VX200 has been tested successfully on the ground, and its core components have even been demonstrated aboard the International Space Station. The real bottleneck, the reason a full-scale interplanetary VASIMR vehicle remains on the drawing board, is its voracious appetite for electrical power. To achieve those game-changing transit times to Mars, a VASIMR engine would need a continuous power supply in the range of hundreds of kilowatts and eventually many megawatts. For comparison, the entire International Space Station, with its massive solar arrays, generates only about 120 kilowatts of power for all its systems. Solar panels simply cannot be made large enough to provide the necessary power for a fast Mars mission. The only practical solution is to pair the VASIMR engine with a compact, lightweight nuclear fission reactor, creating a truly independent and powerful Starship. The development of such a space-rated reactor, while underway in various research programs, represents a monumental technical and political hurdle of its own, involving safety, cost, and public perception. This fundamental bridge between next-generation propulsion and next-generation power generation is the critical path that must be crossed, a challenge that connects directly to the ambitious and controversial projects of the past. From the visionary but peaceful ambitions of VASIMR, we now pivot to a concept born from the darkest depths of the Cold War, a project where the line between defense and annihilation became dangerously blurred. Project Excalibur was not a spacecraft designed for exploration or discovery. It was a weapon system conceived for a single, chilling purpose: to create a global shield by harnessing the most destructive force known to humanity. Emerging from the secretive labs of the Strategic Defense Initiative, popularly nicknamed Star Wars, Excalibur was the brainchild of physicist Edward Teller and his team at Lawrence Livermore National Laboratory. Its operating principle was as radical as it was terrifying. The concept envisioned a device that would be launched into orbit, a platform housing a series of long, slender laser rods. The key, however, was its power source. Unlike any laser before or since, Excalibur was designed to be pumped into existence by the detonation of a nuclear warhead. In a flash of atomic fire, the intense X-ray radiation from the explosion would be captured and channeled down these rods, amplifying into multiple, coherent beams of unimaginable power. These beams would then lash out at speeds impossible to evade, theoretically vaporizing enemy nuclear missiles in the boost phase, just minutes after their launch, far above the Earth's atmosphere. It was the ultimate expression of using a sword to stop a spear, a system intended to render nuclear weapons obsolete by turning them against themselves. The sheer audacity of the physics involved pushed the boundaries of known science. Creating an X-ray laser is an immense challenge because X-rays tend to pass straight through most materials instead of being reflected and amplified like visible light. The Excalibur team proposed using the intense, brief pulse of X-rays from a nuclear explosion to energize a lasing medium made of metal rods, likely composed of elements like selenium or yttrium. The physics suggested that as the X-rays flooded the rods, the atoms within would be excited and then almost instantly release that energy in the form of a focused, high-energy X-ray laser beam. The entire sequence from nuclear detonation to laser firing would have to occur in a fraction of a microsecond. This was not a weapon of sustained bombardment. It was a single, fleeting, and cataclysmic flash of directed energy, a death ray born from a miniature star. The research pushed forward into highly classified testing, with a series of underground nuclear experiments conducted to prove the principle. While the laboratory claimed some successes, the technology ultimately proved far more difficult to master than the initial theories suggested. The beams were not as powerful or as focused as required, and the entire apparatus was wildly impractical, a one-time use weapon of staggering cost and complexity that would have littered space with the radioactive debris of its own power source. Beyond the daunting technical hurdles, Project Excalibur collapsed under the weight of its own profound political and ethical implications. The very idea of a nuclear-pumped laser in space violated multiple international treaties, including the Outer Space Treaty of 1967, which prohibited placing weapons of mass destruction in orbit. The prospect of a single nation deploying a constellation of these devices created a terrifying first strike scenario, destabilizing the delicate balance of mutually assured destruction that had, in a perverse way, kept the peace for decades. If one side believed it could reliably shoot down the other's retaliatory strike, it might be tempted to launch a first attack, plunging the world into nuclear war. Furthermore, the system's effectiveness was widely doubted by scientists outside the program, who pointed out that simple countermeasures like spinning the missiles or deploying cheap decoy balloons could easily overwhelm the limited number of laser beams. As the 1980s drew to a close, the political landscape shifted dramatically. The Cold War began to thaw, the Berlin Wall fell, and the Soviet Union dissolved. The immense political will and astronomical funding required for a system like Excalibur evaporated almost overnight. The perceived threat diminished, and with it, the justification for weaponizing the heavens with such a terrifying instrument. The project was quietly shelved, a relic of a bygone era of existential confrontation. Yet the legacy of this shelved weapon is a complex and paradoxical one. While its primary goal was never realized, the intense research and development effort behind Project Excalibur inadvertently propelled several fields of science forward. The quest to understand and manipulate X-rays for this purpose led to significant advances in plasma physics, nuclear physics, and the fundamental science of laser-matter interactions. The computational models developed to simulate the behavior of matter under such extreme conditions have found applications in other areas, from inertial confinement fusion research to astrophysics, helping scientists model the behavior of stars and supernova. The research into creating and focusing high-energy beams contributed to the development of advanced X-ray sources used today in medicine for sophisticated cancer treatments and in materials science for analyzing the atomic structure of new compounds. The story of Excalibur serves as a powerful, cautionary tale about the dual-use nature of technology, demonstrating how the same knowledge that could have been used to create an orbital doomsday weapon has also, in a more peaceful context, helped save lives and expand our understanding of the universe. This theme of high-stakes military research yielding unexpected civilian benefits is a thread that continues as we examine concepts that sought to replace destructive power with the gentle, persistent push of light itself. While the VASIMR engine offers intelligent control and the Bussard Ramjet dreamed of infinite fuel, another concept sought to achieve high speeds through a far more elegant and minimalist principle, trading complex machinery for a simple, ethereal sheet. This was the solar Moth sail, a vision of propulsion that removed the engine entirely. Envision a spacecraft that glides through the cosmos not with fiery exhaust, but by catching the gentle, persistent push of light itself. The basic idea of a solar sail has been around for centuries, first hinted at by the great astronomer Johannes Kepler when he observed that a comet's tail always points away from the sun, suggesting that sunlight exerted a physical force. A solar sail is essentially a gigantic, incredibly thin, and highly reflective mirror. When photons, the particles of light, strike this mirror, they bounce off, transferring a tiny amount of their momentum to the sail. This push is infinitesimally small, you couldn't feel it on your hand, but in the frictionless vacuum of space, with no air resistance to slow it down, that constant, unending pressure from the sun accumulates day after day, year after year, allowing a spacecraft to build up tremendous velocity without ever carrying a single drop of fuel. It is the ultimate expression of efficiency, turning the space environment itself into a propulsion system. The solar Moth concept, however, took this beautiful idea and supercharged it for practical, high-speed travel within our solar system. A traditional solar sail is a passive device entirely dependent on the sun's natural light, which grows dramatically weaker the farther you travel from its warmth. The solar Moth ingeniously solved this problem by carrying its own sun along for the ride. The concept involved a two-part system: the sail-equipped spacecraft itself, and a colossal, fixed laser array stationed in orbit around the Earth or the Sun. Instead of relying solely on the diminishing sunlight, the sail would be illuminated by a powerful, tightly focused beam from this laser, providing a constant, high-intensity push regardless of the spacecraft's distance from the Sun. This transformed the sail from a passive drifter into a laser-powered vessel, capable of much higher acceleration and offering unprecedented control. Mission planners could turn the laser on and off or adjust its power to carefully manage the spacecraft's speed and trajectory. This hybrid system promised to make fast trips to the outer planets a reality. A journey to Jupiter, which can take 5 or more years with conventional propulsion, could potentially be cut down to just a couple of years with a powerful laser-powered sail, opening up the icy moons of the gas giants for more frequent and responsive exploration. The engineering required to make this dream a reality, however, was where the concept collided with monumental, perhaps even insurmountable, challenges. The first and most daunting hurdle was the laser itself. To provide a meaningful push across millions of miles of space, the laser array would need to be unimaginably powerful, operating in the range of gigawatts equivalent to the output of several large nuclear power plants, and it would have to maintain that beam with near-perfect precision. Aiming a laser beam at a sail the size of a city block that is billions of miles away and moving at tens of thousands of miles per hour is a feat of optical engineering that defies belief. The slightest jitter or misalignment in the laser would cause the beam to miss the sail entirely, leaving the spacecraft adrift. The second colossal challenge was the sail material itself. To be effective, the sail must be extraordinarily large, often envisioned as spanning kilometers across, yet it must also be incredibly thin and lightweight, thinner than a human hair, to minimize mass and maximize acceleration. This gossamer thin film, however, would have to withstand the intense power of the gigawatt laser beam without melting, tearing, or developing wrinkles that would distort its shape and ruin its ability to reflect light perfectly. creating a material that was simultaneously vast, ultra-light, incredibly strong, and optically perfect was a material science challenge that remained far beyond our capabilities. As a result, the solar moth concept, in its full laser-powered glory, was ultimately shelved. The required technologies for the laser and the sail were simply too immature, and the projected cost of building such an infrastructure was astronomical without a clear, immediate mission to justify the expense. Yet the legacy of this shelved concept is profoundly alive and well. The fundamental research into solar sailing that it helped to inspire did not go to waste. It paved the way for a new generation of simpler, sunlight-powered sails that have proven the technology's validity in actual space missions. The Japanese spacecraft Icarus successfully demonstrated solar sail propulsion in interplanetary space in 2010, and the Planetary Society's Light Sail 2 mission has been maneuvering in Earth orbit using only the pressure of sunlight, a beautiful and triumphant proof of principle. These modern missions are the direct descendants of the ambitious solar moth, demonstrating that while the grand vision of a laser-powered sail may have been too ambitious for its time, the core dream of sailing on light was not only sound but achievable. The pursuit of this elegant, fuel-less propulsion continues to captivate engineers, offering a whisper of a future where our spacecraft glides silently between worlds, driven by nothing more than the gentle, timeless pressure of starlight. But the dream of reaching the moon was not always driven by a quest for pure scientific knowledge or human exploration. In a starkly different vision for our future in space, one where the lunar surface would become a new high ground for terrestrial conflict, the United States Army developed a top-secret plan in 1959 known as Project Horizon. This was not a proposal for a scientific outpost. It was a detailed blueprint for a permanent, fortified military base on the moon, a literal garrison designed to establish and maintain what its documents coldly termed military superiority in space. At the height of the Cold War, with the terrifying specter of nuclear annihilation looming over the planet, military strategists were already looking beyond the atmosphere, convinced that the nation that controlled the moon would control the Earth. This was a future where the peaceful, silvery orb in our night sky would be transformed into an armed fortress, a direct extension of the geopolitical tensions that defined the era. The scale and ambition of Project Horizon were breathtaking in their militaristic detail. The plan called for the construction of a sprawling underground complex, built to house a permanent crew of 12 Army personnel. These would not be astronauts in the civilian sense, but soldiers trained for lunar warfare and survival in an utterly hostile environment. The initial base was designed to be self-sufficient, with its own nuclear reactor for power, sophisticated life support systems to recycle air and water, and heavily shielded living quarters to protect the crew from solar radiation and the extreme temperature swings of the 2-week-long lunar day and night. The construction plan was a logistical nightmare, requiring a staggering 149 rocket launches using the nascent Saturn rocket system, which was still in its early development stages, to deliver all the modules, equipment, and supplies needed to assemble the base piece by piece on the lunar surface. This was not a modest flag-planting expedition. It was a full-scale military occupation of another world, intended to be a permanent foothold from which the United States could project its power across the cislunar sphere. The stated purposes of this lunar garrison were as chilling as they were clear. The primary mission was surveillance. From its vantage point on the moon, the Horizon base would have an unobstructed view of nearly an entire hemisphere of the Earth, allowing its crew to monitor global military activities, track missile launches, and conduct detailed reconnaissance of both allied and adversary nations with powerful telescopes and sensors. This would provide an intelligence-gathering capability far beyond anything possible with satellites in low Earth orbit, but the plan went far beyond mere observation. The most controversial and alarming aspect of Project Horizon was its offensive potential. The base was explicitly designed to serve as a launch platform for nuclear-armed missiles. The concept was that missiles launched from the Moon would have a significant strategic advantage. They could bypass most of the early warning radar systems and anti-ballistic missile defenses of the time, falling onto targets on Earth with virtually no warning. The base was also envisioned as a defensive outpost, equipped with weapons to destroy any enemy satellites or spacecraft that might threaten American assets in space. It was the ultimate expression of Cold War paranoia, a plan to extend the doctrine of mutually assured destruction off our planet and onto the lunar surface. So why was this formidable plan for a lunar army never realized? The downfall of Project Horizon was a combination of overwhelming practical challenges and a pivotal shift in national policy. The sheer cost was prohibitive, with estimates running into the tens of billions of dollars even in 1950s currency, a price tag that would have dwarfed the eventual Apollo program. The technological hurdles were also immense. The Army had little experience with the complexities of human spaceflight, and the idea of conducting over 100 successful Saturn rocket launches to build the base was wildly optimistic. But the most significant factor was a decisive political battle over the very soul of the American space program, a powerful faction within the government led by President Dwight D. Eisenhower argued vehemently that space should be a peaceful domain for all humanity, not a new arena for warfare. They believed that the immense prestige of space exploration should be led by a civilian agency, not the military. This vision won the day, leading to the creation of NASA and the consolidation of human spaceflight efforts under the civilian Apollo program. Project Horizon was quietly shelved, its classified reports filed away as a historical curiosity. The legacy of this shelved concept is profoundly significant. Project Horizon serves as a stark and sobering reminder of the divergent paths that space exploration could have taken. It represents a future thankfully avoided, a path where the first human outpost on another world would have been a military installation, setting a precedent for the weaponization of space that might have been impossible to reverse. The decision to choose the civilian, scientific path of Apollo over the militarized vision of Horizon was a monumental one. It helped to establish the foundational principle, later enshrined in the Outer Space Treaty of 1967, that celestial bodies shall be used exclusively for peaceful purposes. While military technology and satellites have always played a role in space, the fact that human presence has been led by scientists and explorers, not soldiers, has shaped the international perception of space as a global commons for discovery. The ghost of Project Horizon reminds us that the greatest challenges in reaching the stars are not always technological, but often ethical, forcing us to continually choose between the darker impulses of our nature and the higher aspiration to explore as a unified human species. Now we arrive at a concept that redefines the very scale of interstellar ambition, shrinking the spacecraft from a city-sized ark to something you could hold in the palm of your hand. Welcome to Project Starshot, an initiative that dares to ask a radical question. Instead of sending one massive, complex starship on a millennia-long journey, why not send 1,000 tiny, simple probes on a sprint that lasts just decades? This is the core philosophy behind Breakthrough Starshot, a vision that trades the traditional rocket for a light sail and replaces a roaring engine with a silent, colossal beam of light. The mission profile is as straightforward as it is revolutionary. Launch a mothership carrying a swarm of star chips into a high Earth orbit. Each star chip is a fully functional spacecraft, but it weighs little more than a paperclip, a gram-scale marvel of miniaturization. Attached to each one is a light sail, a wafer-thin, reflective sheet no larger than a sailboat's mainsail. Once deployed, this tiny craft would then face its source of propulsion, a vast ground-based laser array, a phalanx of beams combined into a single, incredibly powerful push. This isn't a gentle nudge, it's a cannon shot. The plan is to unleash this laser blast for just a few minutes, but in that brief, furious burst, the light sail would be accelerated with a force thousands of times greater than Earth's gravity, reaching an almost inconceivable 20% of the speed of light in a breathtakingly short time. Consider for a moment the sheer velocity involved. 20% of light speed is over 134 million miles per hour. At that pace, a journey to our nearest stellar neighbor, the Alpha Centauri system, which lies 4.37 light-years away, would take just about 22 years. For the first time in human history, a mission to another star becomes a tangible prospect that could deliver results within a single human lifetime, not over centuries. The fly by itself would be a fleeting event, a high-speed dash past any planets in that system lasting only minutes, but the data collected would be priceless. Each nanocraft would be equipped with a suite of microscopic instruments, tiny cameras to snap the first ever direct images of an exoplanet, magnetometers to measure magnetic fields, and spectrometers to analyze the composition of any atmospheres it whizzes past. Primary goal is a straightforward but profound one: to confirm the existence and study the environment of Proxima Centauri b, a rocky, Earth-sized world orbiting within its star's habitable zone, and to see if any of its siblings in the system also hold promise. This would be humanity's first postcard from another star, a brief, glorious transmission sent back across the immense void. The technological hurdles standing between this dream and reality, however, are not just high, they are monumental, representing the absolute cutting edge of multiple scientific disciplines. The first and perhaps most daunting challenge is the laser array itself. To achieve the necessary acceleration, the system would need to generate a coherent light beam with a collective power of roughly 100 gigawatts, focusing it with nanometer precision on a sail that is billions of miles away and receding at a phenomenal speed. Building such an array is likened to scaling up the entire global internet's data traffic and focusing it into a single beam of light for several minutes at a time. The second challenge is the light sail. It must be almost perfectly reflective because any energy it absorbs from the laser, even a tiny fraction, would instantly vaporize it. It needs to be incredibly large to catch enough of the beam, yet impossibly light and strong enough to withstand thousands of Gs of acceleration without ripping apart. Researchers are exploring metamaterials and novel two-dimensional compounds like graphene to create a sail that is only a few hundred atoms thick. The third great obstacle is the star chip itself. Packing all the necessary systems, power, computation, navigation, and communication into a gram requires a revolution in nanotechnology. It needs a robust computer, a tiny but powerful laser for data transmission back to Earth, and a power source, all hardened to survive a 20-year journey through the radiation-filled interstellar medium. Because of these staggering challenges, the full-scale Starshot mission is, for all practical purposes, shelved for the foreseeable future. While the Breakthrough Initiatives Foundation continues to fund vital research and development into each of these key technologies, the actual construction of the 100-gigawatt laser array and the launch of the Nanocraft fleet remains a hypothetical, a vision awaiting a series of fundamental breakthroughs. The project is shelved not for a lack of will or imagination, but due to the sheer scale of the engineering and the astronomical funding required, estimated to be in the range of $5 to $10 billion. It represents the current frontier of interstellar thought, a concept that has pushed scientists to confront the practical limits of miniaturization and photonic propulsion in a way no previous idea has. Starshot serves as a powerful symbol, demonstrating that the greatest barrier to reaching the stars may not be the vast distances themselves, but our ability to think small, to master the realm of the tiny in order to conquer the immense. This philosophy of radical simplification and novel landing techniques was also at the heart of our next concept, which took a similarly unconventional approach to getting back to Earth. Amid the race to reinvent space access in the 1990s, one company dared to propose a solution that looked less like a rocket and more like a fantastical fusion of a missile and a helicopter. The rotary rocket company's Roton ATV was, without question, one of the most bizarre and visually striking spacecraft concepts ever to leave the drawing board. Its entire philosophy was built around a single, radical idea for solving the problem of re-entry and landing. While every other reusable vehicle concept relied on wings like the Space Shuttle or parachutes and retro-rockets like modern capsules, the Roton proposed an entirely different method, a massive helicopter-like rotor mounted on its nose. During its fiery descent back through the atmosphere, this rotor would not be powered by an engine. Instead, it would enter a state called autorotation. This is the same principle that allows a helicopter to land safely even after a complete engine failure. As the vehicle falls, air rushing up through the rotor causes it to spin, generating lift and slowing the descent dramatically. The Roton was designed to use this natural aerodynamic phenomenon to transform a meteoric plunge into a controlled, gentle helicopter-style touchdown, settling softly on its landing legs anywhere a helicopter could land, without needing a runway or a vast ocean for recovery. It was a concept that promised unparalleled operational flexibility, and a landing so gentle it could theoretically be refueled and reflown with minimal turnaround. The vehicle's design was a study in audacious engineering. It stood about 64 feet tall, with a conical shape that gave it the appearance of a classic rocket, but its most striking feature was the complex rotor assembly at the top, housed under a protective shroud during launch. For the ascent to orbit, the Roton would function as a conventional, though innovative, rocket. Its proposed engine was a unique hybrid system that used a rotating bank of 72 small combustion chambers, all fed by a single, centrally mounted turbopump. This spinning engine design was intended to simplify the complex plumbing of traditional rocket engines and improve efficiency. The Roton was conceived as a true single-stage to orbit vehicle, meaning it would carry all its propellant from liftoff and would not jettison any booster stages along the way. After completing its mission in space, it would re-enter the atmosphere nose first. Once it had slowed sufficiently in the lower, thicker air, the protective shroud would be jettisoned, and the enormous rotor blades would unfold and lock into place. From that moment on, the pilots would essentially be flying a giant, descending helicopter, using the rotor's cyclic and collective controls to steer to a precise landing spot and cushion their final touchdown. This combination of rocket and rotorcraft technologies was a bold attempt to create a fully reusable spaceship that could take off from and land at virtually any suitably sized port. Driven by the charismatic and optimistic entrepreneur Gary Hudson, the Rotary Rocket Company made remarkable progress in a very short time. They secured funding, assembled a team of seasoned engineers, and in a display of incredible ambition, they actually constructed a full-scale atmospheric test vehicle. Known as the Roton COC, or Crude Orbital Capsule, this test article was a towering silver prototype equipped with the actual rotor system, but powered by conventional helicopter engines for its flight tests, as the complex rocket engine was still in development. In 2099, this incredible machine began a series of flight tests at the Mojave Air and Spaceport. The world watched as this strange, rocket-shaped object, crowned with a spinning rotor, lifted off vertically, hovered, translated sideways, and landed with the precision of a helicopter. It was a stunning visual, a tangible piece of the future that seemed to prove the fundamental soundness of the landing concept. For a brief, shining moment, it appeared that a small, plucky startup might actually succeed where aerospace giants had hesitated, cracking the code on a completely novel and highly operable launch system. However, the dream was ultimately undone by the harsh convergence of technical reality and financial gravity. The Roton's greatest strength, its radical innovation, was also its greatest weakness. While the atmospheric tests proved the rotor landing system worked beautifully, the heart of the vehicle, its revolutionary rotating rocket engine, remained a formidable and unproven challenge. Developing a brand new, high-performance rocket engine is one of the most difficult and expensive endeavors in all of engineering, and the Roton's unique design added layers of complexity that had never been tackled before. Simultaneously, the broader financial climate for space startups at the turn of the millennium was cooling rapidly. The dot-com bubble was beginning to deflate, and investors were becoming wary of high-risk, capital-intensive ventures. Rotary Rocket Company burned through its funding faster than anticipated, struggling to attract the additional hundreds of millions of dollars needed to complete the engine development and attempt an orbital flight. With the money running out and the technical hurdles still looming large, the company was forced to declare bankruptcy in 2001. The full-scale Roton test vehicle was eventually sold for scrap, a poignant end to one of the most visually imaginative spacecraft projects of the modern era. The legacy of the Roton is not one of pure failure, but rather a powerful case study in the perils of pioneering. Its collapse highlighted the immense financial and technical risks inherent in attempting to leapfrog established aerospace paradigms with a completely novel architecture. The project demonstrated that while a brilliant and novel idea can capture the imagination and even achieve partial success in testing, the path from a prototype to a reliable, orbital-class vehicle is a chasm that requires vast amounts of capital and relentless technical execution. The lessons from the Roton's demise were absorbed by the next generation of private space companies. Entrepreneurs like Elon Musk at SpaceX and Jeff Bezos at Blue Origin adopted a more incremental, iterative approach. Instead of trying to solve every problem with a single, revolutionary vehicle, they focused on perfecting individual technologies step by step, starting with simpler, more conventional rocket designs and then gradually introducing reusability. The Roton story serves as a testament to both the boldness of human imagination and the sobering realities of engineering and finance, a reminder that the road to orbit is paved with brilliant concepts that dared to be different, even if they fell just short of the final frontier. Imagine a spaceplane that didn't need a colossal launch complex, but instead operated with the flexible, rapid response ethos of a fighter jet. This was the core ambition of the Black Horse transatmospheric vehicle, a sleek and cunning concept from the United States Air Force in the 1990s. While other designs sought power through sheer size or revolutionary engines, Black Horse employed a brilliant tactical trick to conquer the rocket equation. It would borrow its breath from the sky itself. The operational plan was as daring as a military operation. The vehicle would take off from a standard runway using a conventional jet engine, burning standard jet fuel. But here was the masterstroke: it would not carry its liquid oxygen oxidizer, the heavy chemical partner needed for rocket combustion, from the ground. Instead, after reaching a high altitude, the Black Horse would perform a delicate, high-stakes rendezvous with a modified aerial tanker aircraft, not unlike the mid-air refueling operations that are routine for bombers and fighters. In a carefully choreographed ballet, the tanker would transfer a full load of supercold liquid oxygen into the spaceplane's waiting tanks. Once this cryogenic fuel was loaded, the Black Horse would then ignite its rocket engine, combining the newly acquired oxygen with its onboard fuel to make the final, powerful leap from the upper atmosphere into orbit. It was a two-step dance to space, designed to outsmart gravity through logistics rather than brute force. The engineering logic behind this aerial refueling scheme was profoundly clever. The single greatest mass in any rocket launching from Earth is not the payload or the structure, but the oxidizer needed for the burn. By leaving that heavy liquid oxygen on the ground and only picking it up once already airborne and high in the atmosphere, the Black Horse vehicle could be dramatically smaller, lighter, and cheaper to operate. It essentially used the atmosphere itself as a temporary storage tank, allowing the craft to be lean and efficient for its initial climb. This design philosophy made it perfect for the Air Force's specific desire for responsive space access. The vision was a fleet of these small, reusable spaceplanes kept on alert, capable of launching on very short notice to rapidly replace a critical military satellite destroyed in a conflict or to deploy new surveillance assets in a crisis. It promised a level of flexibility and resilience that large, ground-launched rockets, which require lengthy preparation and fixed infrastructure, could never hope to match. The Black Horse was not meant for grand exploration. It was conceived as a quick reaction force for the ultimate high ground, a spaceplane that could serve as a tactical tool for national security. Ultimately, despite its elegant and promising premise, the Black Horse program was grounded before any metal was cut. The cancellation came from a familiar confluence of shifting priorities and stubborn technical realities. As the Cold War ended, the immediate pressure for advanced military space systems lessened, and the Air Force's budget and focus shifted to other domains. The technical challenges, however, were the true showstoppers. Transferring cryogenic liquids like liquid oxygen in mid-flight is an immensely difficult problem. Liquid oxygen must be kept at extremely low temperatures, around -297 degrees Fahrenheit, and it constantly boils off into gas. Designing a transfer system that could connect two aircraft flying in close formation, pump a supercold and volatile fluid quickly and safely without freezing the mechanisms or causing dangerous pressure buildups, and then disengage cleanly, was a nightmare of aerospace plumbing. The technology for such a complex cryogenic transfer in the dynamic environment of flight simply did not exist at the required level of reliability in the 1990s. The risks were deemed too high and the development costs too great for the uncertain payoff. Yet, the legacy of the shelved Black Horse concept is a powerful testament to how a single innovative idea can propagate, influencing a whole family of related technologies. While the specific method of mid-air oxidizer transfer proved too difficult, the core principle of making launches more efficient and flexible by starting from the air lived on. We see its intellectual descendants in the various air launch systems that have been developed since. Virgin Galactic's White Knight II carrier aircraft, for instance, lifts the smaller Spaceship II to a high altitude before release, giving the spaceplane a major head start in velocity and altitude without having to fight through the thickest part of the atmosphere. Similarly, Northrop Grumman's Pegasus rocket is carried aloft by a modified Lockheed L-1001 airliner and dropped before igniting its engines. These systems achieve some of the same goals Black Horse aimed for: operational flexibility and reduced fuel requirements, by carrying the entire rocket to altitude rather than just its oxidizer. The dream of a fully reusable, runway-to-orbit vehicle that could refuel in flight continues to inspire designers, proving that even when a specific concept is shelved, the spark of its innovation can light the way for others, creating a branching tree of technological progress where no single idea is ever truly lost. Just as the Black Horse concept reimagined launch logistics, another pivotal collaboration was quietly taking shape in orbit, one that would redefine international relations in space. The story of the International Space Station as we know it today was not a foregone conclusion. It emerged from the ashes of two separate and competing station programs, one American and one Russian, that were forced together by the tectonic political shifts of the early 1990s. Before the iconic truss structures and solar arrays of the ISS graced our skies, NASA was deep into the development of its own station, named Freedom. Conceived during the Reagan administration, Freedom was a complex, massive structure designed to be a symbol of American technological preeminence, a permanent outpost built with the help of allies in Europe, Japan, and Canada. Simultaneously, on the other side of the fading Iron Curtain, Russian engineers were drafting plans for Mir 2, a successor to their venerable and highly successful Mir station. Mir 2 was designed to be a more modern and capable platform, learning from the hard-won lessons of long-duration spaceflight aboard its predecessor. It featured plans for new, larger modules and a more robust power system, envisioning a future where Russia would continue its independent leadership in orbital operations. For a time, it seemed two separate spacefaring civilizations were preparing to build their own distinct cities in the sky, a reflection of the Cold War division that had defined the previous half-century. The collapse of the Soviet Union in 1991 changed everything almost overnight. The Russian economy went into freefall, and its once mighty space program found itself on the brink of collapse, struggling to pay its engineers and cosmonauts. The ambitious Mir 2 project, which required a steady and significant financial river to become reality, was suddenly an unaffordable dream. At the same time, NASA Freedom Station was facing its own existential crisis. Plagued by ballooning costs, design complexities, and criticism from Congress, the project was repeatedly scaled back, earning the unflattering nickname Fred in some circles, a skeletal version of its original grand vision. It was in this atmosphere of mutual desperation and opportunity that a radical idea was born. Instead of two struggling nations building two separate, expensive stations, what if they combined their efforts, their expertise, and their blueprints into a single, truly international project? This was not a decision born solely of idealism. It was a pragmatic masterstroke. For the United States, bringing Russia into the fold was a strategic move. It provided a peaceful, high-profile outlet for the brilliant but underemployed Russian aerospace engineers who might otherwise have been tempted to sell their expertise to unstable regimes. It also gave NASA immediate, invaluable access to Russia's profound experience with long-duration spaceflight, an area where they were the undisputed world leaders. For Russia, it was a financial and political lifeline, a way to keep their space program alive and maintain their status as a major space power. The design for the Russian Mir 2 station was not simply thrown away. Its very heart was transplanted into the new International Space Station. The most critical contribution was the Zvezda service module, which was originally constructed to be the core of the standalone Mir 2. When you look at the ISS today, Zvezda is the central, beating heart of the Russian segment, providing the station's early living quarters, life support systems, and its primary propulsion. Without this ready-made module, the assembly of the International Space Station would have been delayed by years, requiring NASA to design and build a similarly complex component from scratch. The entire Russian segment's design philosophy, with its emphasis on modular expansion and robust, automated cargo and crew delivery via Soyuz and Progress spacecraft, is a direct inheritance from the Mir and Mir-2 programs. This merger was not just about hardware, it was a fusion of two very different engineering cultures. American modules were typically delivered fully assembled in the space shuttle's cargo bay, while Russian modules were designed to launch on rockets and self-dock autonomously. Integrating these two distinct technological ecosystems was one of the greatest engineering diplomacy challenges ever undertaken, requiring a decade of careful planning, translation of countless technical documents, and the building of trust between former adversaries. The abandonment of the standalone Mir-2 station, therefore, represents one of the most significant and positive what-if scenarios in the history of space exploration. Had the Soviet Union not dissolved, we might be living in a world with two large, competing space stations in orbit, a constant reminder of a divided world. The financial strain of maintaining the aging Mir station while trying to build Mir-2 would have likely crippled the Russian program, potentially leading to its total collapse. The decision to merge the projects into the International Space Station was a triumph of pragmatic geopolitics over nationalistic pride. It transformed a potential symbol of renewed competition into the greatest peacetime collaborative project in human history, a shining orbital laboratory that has hosted astronauts from 19 nations. The shelving of Mir-2 was not a failure, but a necessary sacrifice that paved the way for an unprecedented era of international cooperation, proving that the harsh environment of space could be a powerful catalyst for unity on Earth. This spirit of turning weapons of war into tools of science finds an even starker contrast in our next concept, which explored the very outer limits of what should never be attempted. From the collaborative triumph of the International Space Station, we now turn to a concept that represents the absolute antithesis of that spirit, a plan so chilling it forces us to confront the darkest impulses that could have been exported from Earth into the cosmos. Project 119 was not a mission of exploration or a blueprint for a vessel. It was a secret study commissioned by the United States Air Force in the late 1950s with a single, staggering objective: to detonate a nuclear weapon on the surface of the Moon. In the fevered climate of the Cold War, where every technological achievement was a pawn in a global game of geopolitical chess, the primary motivation was a stark and simple demonstration of power. The thinking was brutally pragmatic. What greater symbol of national prowess could there be than to create a man-made, atomic flash visible to the entire world on the face of our celestial neighbor? It was the ultimate flex of military muscle, a plan to literally paint the Moon with the fire of human conflict and show the Soviet Union that American reach extended not just across the globe, but all the way into the heavens themselves. The scientific work behind this terrifying proposal was ironically conducted with cold, clinical precision. A team of researchers, assembled under the veil of secrecy, was tasked with determining the feasibility and, most critically, the visibility of such a detonation. Among these scientists was a young doctoral student named Carl Sagan, who would later become one of the most beloved and influential voices for planetary science and cosmic wonder. His role in Project 119 was to model the behavior of the dust and gas that would be ejected by the nuclear explosion. The key question was whether the resulting mushroom cloud, illuminated by the sun in the airless void, would be large and bright enough to be seen with the naked eye from Earth. Sagan's calculations focused on the physics of the lunar ejector, working out how the explosion would lift material off the surface and how sunlight would scatter through it to create a visible glow. The profound irony is almost unbearable. The same mind that would later describe Earth as a pale blue dot and plead for the preservation of our fragile world was once enlisted to calculate the optics of its most destructive weapon being used to scar another. This juxtaposition serves as a powerful reminder that the path of science is not always straight, and that even the most visionary thinkers can be swept into the service of nationalistic fervor. The technical and logistical challenges of Project A119 were as immense as the ethical ones. The plan involved launching a missile carrying a nuclear warhead on a direct trajectory to the Moon, where it would impact the surface and detonate. There would be no landing, no soft touchdown. It was a kinetic impactor with an atomic payload. Scientists debated the ideal location for the blast, with many arguing for the Terminator line, the border between the Moon's day and night sides, where the contrast between the dark lunar surface and the brilliant flash of the explosion would be most dramatic for viewers on Earth. They estimated that a mushroom cloud of vaporized rock and dust could potentially be visible for up to a minute, a fleeting but terrifying spectacle in the night sky. The entire undertaking was a grotesque perversion of the scientific method, using physics not to understand the universe, but to stage a cosmic fireworks display whose primary data point would be the level of fear it instilled in a global audience. It was astrophysics weaponized, a plan to turn our greatest natural satellite into a billboard for annihilation. Ultimately, and to the immense relief of history, Project A119 was shelved and never advanced beyond the theoretical study phase. The reasons for its cancellation were a mixture of practical risk and dawning ethical awareness. From a strategic standpoint, the Air Force began to fear a potential public relations disaster. What if the mission failed, a missile malfunctioning and crashing back to Earth with a live nuclear warhead, or missing the Moon entirely, would be a catastrophic embarrassment. There was also the sobering realization that such a provocative act could escalate tensions with the Soviet Union to a dangerous and unpredictable level, potentially triggering a response that could spiral out of control. But perhaps the most significant factor was a growing consensus within the scientific and political communities that the Moon, and space in general, should be treated as a realm for peaceful exploration, not warfare. The very idea of nuclear testing on a pristine celestial body began to be seen for what it was, a scientific and ethical abomination. The project was formally cancelled in early 1959, its files classified and tucked away, a secret shame that would not be fully revealed for decades. The legacy of this shelved concept is profoundly cautionary. Project A119 stands as a stark monument to a path not taken, a chilling reminder of how easily the high frontier of space could have been transformed into the ultimate battlefield. Its existence proves that the line between exploration and domination, between wonder and warfare, is perilously thin. The fact that cooler heads prevailed and the project was abandoned helped to set a crucial precedent, reinforcing the principle that would later be codified in the 1967 Outer Space Treaty, which explicitly bans the placement of nuclear weapons and other weapons of mass destruction in orbit or on celestial bodies. The ghost of Project A119 serves as a permanent warning, urging us to continually choose the path of knowledge and cooperation over the path of fear and demonstration. It forces us to ask what kind of legacy we wish to leave in the cosmos, one of scars and shadows, or one of discovery and unity. This sobering reflection on the peaceful use of space finds a powerful counterpoint in our next concept, which also harnessed the power of the atom, but with the noble and clear-eyed goal of pushing humanity toward the planets. While the roar of the Saturn V's chemical engines had successfully carried humanity to the Moon, a quieter, more powerful revolution was already taking shape here on Earth, promising to open the entire inner solar system to human exploration. In the shadow of Apollo's triumph, NASA and the Atomic Energy Commission embarked on a daring partnership known as the Nuclear Engine for Rocket Vehicle Application, or NERVA. This was not a paper concept or a far future dream. This was a full-scale, hardware-rich development program that produced the most advanced rocket engine ever built, an engine that ran not on chemical combustion, but on the controlled fury of a miniature sun. The principle behind a nuclear thermal rocket is one of breathtaking efficiency. Imagine replacing the complex, explosive burning of fuel and oxidizer in a conventional engine with a far simpler and more powerful process. Inside a NERVA engine, a compact nuclear fission reactor, not much larger than a trash can, would be brought to criticality. Through this superheated core, a propellant, typically liquid hydrogen, the lightest and most effective material for the job, would be pumped. The hydrogen wouldn't undergo a chemical reaction. It would simply be flash heated by the reactor to temperatures exceeding 2,400 degrees Celsius, transforming it into an incandescent, enormously energetic gas that would then blast out of a conventional rocket nozzle. This process leverages the raw thermal energy of nuclear fission, which packs millions of times more energy per unit of mass than any chemical reaction. The result is an engine with nearly double the efficiency or specific impulse of the best chemical rockets, where a Saturn V engine had to carry colossal tanks of both fuel and oxidizer. A NERVA-powered spacecraft could achieve the same velocity change with far less propellant, or use the same amount of propellant to travel much faster and farther. It was the key to turning months-long, grueling interplanetary voyages into swift, manageable expeditions. The success of the NERVA program was nothing short of remarkable. This wasn't a speculative laboratory experiment. It was a robust, ground-up engineering project that resulted in the construction and extensive testing of multiple full-scale flight-ready engines. At the Nevada test site, inside massive, specially constructed facilities, these nuclear engines were fired up repeatedly, proving their reliability and performance under conditions that simulated the vacuum of space. The engineers and scientists working on NERVA weren't just trying to see if the concept worked. They were refining it for operational use. They tested engines like the NRX/XE for hours at a time, far longer than would be needed for a typical Mars burn, and demonstrated the ability to restart them multiple times. They pushed the technology to its limits and found it not only viable but exceptionally robust. The final designs were so advanced that by the early 1970s, the program's director could confidently state that if given the go-ahead, they had a NERVA engine that was ready to fly. It had passed every technical milestone. The data was clear. Nuclear thermal propulsion was no longer a theory. It was a proven, working technology, waiting on the shelf for a mission worthy of its power. The blueprint for that mission was already drawn up. Visionary planners at NASA envisioned a fleet of NERVA-powered vehicles, known as Rift, that would serve as the upper stages for massive interplanetary spacecraft. These nuclear stages would be assembled in Earth orbit, and once ignited, they would provide the sustained thrust needed for fast transits to Mars. A journey that would take a chemical rocket 9 months could be slashed to just 4 or 5 with a NERVA engine, drastically reducing the crew's exposure to cosmic radiation and the debilitating effects of microgravity. The road to Mars in the 1980s was, from a purely technical standpoint, already paved. Yet, despite this stunning technical success, the NERVA program was abruptly terminated in 1972. A casualty of a perfect storm of political, budgetary, and social pressures. The immense cost of the Vietnam War was putting a severe strain on the federal budget, and NASA post-Apollo funding was being slashed dramatically. The national mood had shifted. The fervent, Cold War-driven urgency that propelled the moon landing had dissipated, replaced by a focus on domestic issues and a growing skepticism toward large, expensive technological endeavors. The Nixon administration, facing these pressures, made the fateful decision to cancel the Saturn V rocket production line and to abandon plans for human missions to Mars, focusing instead on the more modest, near-Earth goals of the Space Shuttle program. Without a clear destination like Mars, the raison d'etre for the NERVA engine evaporated. Compounding this was a rising public anxiety surrounding all things nuclear. The environmental movement was gaining momentum, and the idea of launching a live nuclear reactor into space, even though NERVA engines were designed to only be activated in a safe, high orbit, sparked significant public concern and political opposition. The very power source that made the engine so capable also became its greatest political liability. In the end, the plug was pulled not because the technology failed, but because the political and financial will to use it collapsed. The fully developed, flight-ready NERVA engines were placed into storage, and the dream of a nuclear-powered Mars mission in the 20th century was shelved indefinitely. The shelving of NERVA had a profound and lasting impact, effectively placing human exploration of Mars into a deep freeze for decades. The Space Shuttle, while an engineering marvel in its own right, was a vehicle designed for operations in low Earth orbit, a truck for building a space station, not a ship for sailing the interplanetary seas. By choosing the shuttle and canceling NERVA, the United States consciously traded the vast, open horizon of the solar system for an orbital backyard. Every mission architecture study for sending humans to Mars conducted since has repeatedly concluded that nuclear thermal propulsion remains the most viable and efficient method for such a journey. The decades-long delay caused by NERVA cancellation means that we are only now, in the 21st century, restarting the serious development of nuclear thermal rockets, essentially picking up where the program left off 50 years ago. However, NERVA legacy is far from lost. The terabytes of test data, the metallurgical research on high-temperature materials, and the fundamental engineering principles established by the program constitute an invaluable technological foundation. Today, as NASA Draco program and various private companies work to develop a new generation of nuclear thermal rockets, they are not starting from scratch. They are standing on the shoulders of the NERVA engineers, relearning their lessons and validating their data. The shelving of NERVA was a monumental setback, but it was not a permanent defeat. It left behind a proven blueprint for a technology that may yet prove to be the essential workhorse engine for humanity's first journey to the Red Planet, a silent, powerful relic waiting for its moment to finally ignite among the stars. While the United States and Russia were building on their legacies of massive rockets and spaceplanes, another major technological power was quietly developing its own vision for independent and reusable space access. In the 1980s and 90s, Japan's aerospace community embarked on an ambitious journey to create the HOPE spaceplane, an acronym for the H2 orbiting plane. This was not merely a proposal, it was a full-fledged national project aimed at giving Japan its own autonomous runway-to-orbit capability. The vision for HOPE was both practical and sophisticated, an unmanned, fully automated vehicle that would launch vertically atop Japan's powerful new H2 rocket, operate in orbit to deploy satellites or conduct experiments, and then navigate its way back through the atmosphere to make a precise, autonomous landing on a runway, just like an aircraft. It was a statement of intent, a declaration that Japan would not just be a passenger or a contributor on other nations' spacecraft, but a master of its own destiny in space, with a reusable vehicle designed for efficient, routine operations. The design of HOPE evolved significantly throughout its lifetime, reflecting the immense challenge of creating such a vehicle. early concepts depicted a relatively small, lifting bodycraft that would be housed inside a protective shroud during launch. Later iterations grew larger and more complex, with designers grappling with the same brutal physics that challenged every spaceplane project: the tyranny of weight versus heat shielding and payload capacity. The vehicle was envisioned to be constructed from advanced composite materials and equipped with a thermal protection system to withstand the searing heat of re-entry. Its automated guidance, navigation, and control systems were a particular focus of Japanese engineering prowess, intended to handle every phase of the mission from ascent to the delicate final approach and touchdown without any human intervention. This emphasis on autonomy was a key differentiator, positioning HOPE as a highly capable robotic space truck that could service orbital infrastructure or retrieve experiments with minimal ground control. The project moved beyond mere blueprints into tangible testing. A series of scaled flight models, including unpowered gliders and rocket-powered prototypes, were built and flown to validate the aerodynamics and autonomous landing technology. These tests, which saw models dropped from helicopters to execute perfect automated landings, proved that the fundamental flight control systems were sound, bringing the dream of a Japanese spaceplane tantalizingly close to reality. Despite this promising progress and substantial investment, the HOPE project was ultimately shelved. The primary reasons were a sobering combination of financial pressure and a dramatically shifting global context. The development costs for such a cutting-edge, reusable vehicle spiraled upwards, becoming a significant burden even for Japan's robust economy. At the same time, the geopolitical landscape was transformed by the end of the Cold War. The intense, budget-justifying competition between the United States and the Soviet Union evaporated, leading to a global reassessment of expensive, standalone space projects. The launch vehicle market also began to change, with the rise of increasingly reliable and cost-effective expendable rockets, which called into question the economic advantage a reusable spaceplane like HOPE would need to prove. Faced with these realities, Japan made a strategic and pragmatic decision to reallocate its resources. Instead of pursuing an independent spaceplane, the nation chose to funnel its expertise and funding into its contributions to the International Space Station, such as the magnificent Kibo Laboratory Module and the H-2 Transfer Vehicle, or HTV, an automated cargo spacecraft renowned for its precision and reliability. This pivot away from HOPE was not a failure, but a conscious choice to excel in areas that offered more immediate scientific and diplomatic returns. The legacy of the shelved HOPE spaceplane is a poignant and powerful one, representing a path not just for Japan, but for many spacefaring nations in the late 20th century. It embodies the global ambition to achieve independent, reusable access to space, a goal that proved to be a kind of technological summit, incredibly difficult and expensive to conquer. For a time, it was a peak just out of reach for all but the two original superpowers. The knowledge gained from HOPE's development was not wasted. It deeply informed the design of the HTV cargo ship and continues to influence Japanese aerospace research into reusable launch systems. HOPE stands as a testament to a moment when a nation looked to the stars and dared to design its own vehicle to get there, a symbol of a technological ambition that was deferred, but whose spirit continues to inspire the next generation of spaceplane dreams around the world. Looking back across this incredible graveyard of cosmic ambition, a clear and sobering picture begins to form. The stories of these 25 shelved spacecraft are not just a collection of isolated misfortunes. They are chapters in a single, larger story about the immense gap between human imagination and our practical ability to execute. When you trace the threads connecting the cancelled Orion to the abandoned NERVA and the grounded Valkyrie to the never-built Sea Dragon, you find that their downfalls almost always boil down to a handful of powerful, recurring forces. The most dominant of these are the brutal, twin gatekeepers of technological immaturity and staggering cost. Concepts like Project Daedalus were breathtakingly elegant on paper, but they relied on a fundamental mastery of controlled nuclear fusion, a technology that has remained stubbornly just out of reach for over half a century. Similarly, the X-33's revolutionary design was ultimately defeated by the limitations of 1990s composite materials, proving that a brilliant blueprint is useless if the physical substance to build it doesn't yet exist. These weren't failures of imagination, but rather a painful collision with the hard wall of contemporary science and engineering. The necessary pieces of the puzzle simply weren't available at the time, leaving these visionary ideas stranded in a future they were too early to inhabit. Just as daunting was the sheer financial scale of many of these projects, the Sea Dragon was designed to be built in a shipyard because its creators understood that traditional aerospace manufacturing would be far too expensive for something so colossal. The O'Neill cylinder and the Bernal sphere weren't just expensive, they required a level of financial commitment akin to a permanent, global Marshall Plan for space, a multi-trillion-dollar investment that no single government or consortium was prepared to make. This highlights a critical pattern: the grander the vision for humanity's future in space, the more it falls victim to a brutal chicken-and-egg dilemma. We can't build an O'Neill cylinder until we have a thriving space-based economy to justify it, but we can't create that economy without the cheap access to space that a Sea Dragon might have provided. These concepts were often victims of their OWN Chinese letter vision, trapped in a cycle where their immense potential was exactly what made them impossible to fund. They required a leap of faith so large that, in the absence of an immediate, existential threat or an overwhelming political imperative, the financial risk was simply too great for any rational entity to bear. And that political imperative is the third major thread weaving through these stories. The trajectory of space exploration has never been driven by technology alone. It is perpetually tugged and shifted by the powerful currents of geopolitics. The sudden end of the Cold War didn't just conclude an era of tension. It pulled the financial and ideological rug out from under countless programs. The Soviet UR-700M lunar lander wasn't cancelled because it was a bad design, but because the geopolitical race it was built to win was suddenly over. Similarly, the shift in NASA's priorities from deep space exploration to the low Earth orbit focus of the Space Shuttle program directly led to the cancellation of the NERVA engine, a technology that was literally ready to fly to Mars. These projects were not terminated due to technical failure, but because the political landscape transformed, leaving them as orphans without a mission. Their funding vanished not because they were unachievable, but because they no longer served a pressing national or strategic purpose in the eyes of those holding the purse strings. This leads directly to the final and perhaps most subtle common factor: the lack of a clear, immediate, and profitable application. For every military project like the Black Horse spaceplane that was grounded by technical hurdles, there was a commercial or scientific concept like the SPS Alpha solar satellite that simply couldn't answer the fundamental question: who will pay for this and what is the return? In a world of limited resources, concepts that are perceived as long-term scientific curiosities or far-future commercial ventures will always struggle against projects with more immediate, tangible benefits. The Bifrost lunar elevator is a perfect example of an idea that is technically more feasible than an Earth-based space elevator, but it remains on the drawing board because there is not yet a self-sustaining lunar economy to make it a financially sound investment. It is a solution waiting for a problem to emerge. Understanding these recurring themes is not an exercise in cynicism or pessimism. On the contrary, it is an essential act of learning. For the next generation of engineers, entrepreneurs, and visionaries, this history serves as a crucial guidebook. It teaches that a successful spacecraft concept must not only be scientifically sound and brilliantly designed, but it must also navigate the complex realities of political will, economic viability, and technological readiness. The ghosts of these 25 lost dreams are not just monuments to what might have been. They are our most valuable teachers, offering hard-won lessons from the past to illuminate the practical path toward a future we can actually build. And so we reach the end of our tour through this magnificent museum of might-have-beens, a collection of ghost ships that represent the very peak of human ambition. We have ventured together through concepts that could have carried entire cities to Saturn, built worlds inside spinning cylinders, and harnessed the power of stars to sail between them. These were not just machines, they were declarations, blueprints for futures where humanity was no longer confined to its cradle. We dared to envision a solar system bustling with industry, with lunar elevators and orbital power stations, and even to dream of sending our consciousness to another star on a beam of light. These 25 shelved designs are more than just fascinating footnotes in engineering textbooks. They are powerful testaments to our species' unique ability to look at the void and envision a home. The true legacy of these cancelled projects is not measured in the metal that was never forged, but in the knowledge that was irrevocably gained. Every single one of these concepts, from the terrifying power of Orion to the elegant physics of the Bussard Ramjet, forced scientists and engineers to confront the absolute limits of the possible. They pushed the boundaries of material science, thermodynamics, and plasma physics, generating foundational research that has become the bedrock of our modern space efforts. The advanced composites tested for the X-33 informed the development of lighter, stronger satellite components. The intricate calculations for the Daedalus probe refined our models of interstellar travel and fusion dynamics. Even the sobering analysis of why the Bussard Ramjet wouldn't work was a vital contribution, saving future generations from pursuing a scientific dead end. These shelved concepts were not failures. They were the essential, rigorous homework that had to be completed before we could take the next real step. They are the intellectual giants upon whose shoulders every successful mission today quietly stands. This journey perfectly illustrates that the line between science fiction and science fact is not a wall, but a frontier, and it is crossed by the relentless, often thankless pursuit of ideas. For every Starship that launches from a pad in Texas, there are a dozen forgotten Daedalus probes and venture stars that paved its way in the realm of theory and calculation. Progress is not a straight line from dream to reality. It is a messy, iterative process of imagining the extraordinary, testing its limits, and learning from both its successes and its spectacular shortcomings. The philosopher George Bernard Shaw captured this spirit perfectly when he wrote, "You see things, and you say, why? But I dream things that never were, and I say, why not?" This is the essence of engineering and exploration. It is the courage to look at a seemingly insurmountable challenge, the vastness of space, the tyranny of the rocket equation, the loneliness of the void, and to respond not with resignation, but with a blueprint, a calculation, and a defiant, why not? So let this collection of shelved marvels be a permanent reminder to nurture that why not spirit within ourselves and within our society. These concepts challenge us to be more patient with long-term goals, to see the value in pure research, and to understand that today's impractical dream is often the foundation for tomorrow's reality. They teach us that ambition itself is a form of fuel. Now, we would love to hear from you. Looking back at these incredible vessels of imagination, which one do you wish had escaped the archive and roared to life? Was it the oceanic behemoth of the Sea Dragon, promising a solar system open for business, the quiet nuclear torch of the NERVA engine, ready to carry humans to Mars decades ago? Or perhaps the serene, generational voyage of the Innsman Starship, a world setting out for the stars? Let us know your favorite in the comments below. We read every single one. And if you enjoyed this deep dive into the technology that shapes our future, please subscribe to the channel for more journeys to the edges of science and imagination. Thank